Sure. Start out in 2 minutes. Sure. नहीं मतलब क्रिएट सेशन combination launching and stuff.
Additional.
లేదు నేను तुम्ही నా దగ్గర వాట్సాప్ నంబర్ లేదనుకుంటుంది.
morning, students. Sorry for the delay. There are some technical issues. Okay, it was resolved. Okay. Yeah, I'm Shiva Subramaniam. Okay, the faculty of ACE Engineering Academy. So I have my MTech and PhD degree. Okay, I have more than 12 years of teaching experience. Okay, the subject that we are going to consider now, usually we'll refer it as electronic devices. Okay, usually we'll call EDC electronic devices and circuits. Okay, but we are going to deal with the devices actually here. Circuits is the application part where it is going to be dealt in the analog circuits. Okay, so but anyhow, usually we'll call it as electronic devices and circuits, EDC. Okay, but in specific we can say what electronic devices. Okay, now here this subject is going to be common for in case of ESC, if you take, this is common for ECE, triple E, but anyhow instrumentation they have to write the exam in electronics and telecommunication. Okay, and in case of gate if you consider, this is for ECE only, but anyhow this is going to help you if you understand the electronic devices better. Okay, the application part, which is nothing but the analog circuits, you can understand in a very better way. Okay, so please, those who are, I think there are ECE and instrumentation students, I'm specifically telling for instrumentation students, don't think that this subject is not required for you. If you have the basics of this, okay, then you can better perform in the analog circuits or analog electronics. Okay, now for today's lecture, okay, so what we are going to consider here is, okay, we'll give the course introduction. Okay, some basic terminology, definitions and all. Okay, and then we'll discuss what are the different topics that we are going to consider in this. Okay, now before starting the actual syllabus, I want to mention some important points here. Okay, because we are now you are accessing me in a remote way. Okay, not in a physical way, but my electromagnetics teacher Jai Shankar sir used to say one quotation, frequently, very frequently: circumstances may change, but attitude should not be changed. I'll repeat this: circumstances may change, but attitude should not be changed. So as a student, okay, as a student, you are always, okay, your intention is always what? You need to learn the things or subject. Okay, so whatever it may be the circumstances that you are going to have. Okay, so please pay attention. Initially, you just believe me blindly. Whatever I'm explaining here, I'm going to explain here, is going to be required for you. Don't have second thought in your mind. Okay, it is going to be required for you. Slowly, as the subject is going to progress, I want to make you independent from my side. Okay, initially you are completely dependent on me. Okay, and as the subject progresses, you need to be independent. Okay, so in that way I'm going to organize the course. Okay, so each and every point which is going to be even a minute point we are going to discuss, please pay attention. Okay, this is very important one. You need to have dedication and commitment. Okay, if you are missing these two, you are not going to, you cannot achieve anything in your life. Please keep it in mind. Okay, you should have commitment and what? Determination. You should have that. Okay, now if you want to succeed in any competitive exam, there are two factors which are going to decide. The first one is going to be how fast, okay, or speed, okay, how fast you are responding, and the second factor is going to be the accuracy. Please remember, okay, these two factors will decide the rank in any competitive exam. The first one is speed, the second one is the accuracy. So these two things you need to develop, okay, it takes certain time. Okay, it's not going to be like, overnight you are going to, become an efficient person. Okay, it takes certain time, and there we are helping you. Okay, as a faculty, or as an institute, we are trying to help you in these two factors. Okay, the first and foremost important thing is you must listen to the class. Concentration, with concentration you have to listen. Please keep it in mind, don't miss even a single point. Okay, then the second thing is, once you got certain idea, then you need to start practicing the questions. It may be a previous questions or the booklet that has given to you. Okay, start practicing the questions. Only by these things you can improve the speed and accuracy. Please keep it in mind. And these two will decide the rank in the any competitive exam. Okay, so you have to put continuous effort. Okay, it's not like one day you are, studying for 10 hours and then 1 week you are getting relaxed. It's not like that. Okay, it should be a continuous process. Okay, so hope I am clear with what I have, till now I have explained. Okay, now let us get into the basic introduction of this subject, electronic devices. Okay, few definitions we are going to see. Okay, now let us consider, the first thing is, we'll try to classify the materials based on the parameter. Here I'm going to consider is the energy gap. Okay, so what I'm considering, energy gap. So I'm considering classification of materials based on energy gap. Okay, now let us consider, in a certain, material, the energy band diagram is represented something like this. See, what is the, y-axis here? Usually in the energy band diagram, it is the electron energy. Please remember, default, what is the y-axis in the energy band diagram? It is electron energy. So this is electron energy. So default. Okay, even if you are not mentioning, you should take it. Okay, it is the default. Okay. Now, in this one, let us take, this is bottom of the conduction band. Usually will represent with EC. Okay, try to understand the technical words that I am using. Bottom of the conduction band is what? EC, and the top of the valence band is EV. Okay, there will be two bands, valence band and conduction band. Now we can very clearly see that there is an overlap of conduction band and the valence band. So this type of materials usually will refer it as what? Metal. Okay, or semiconductor. Sorry, metal or conductor. Metal or conductor. Okay, so what are the examples? You can give the aluminum, copper, gold, etc. Okay, now let us consider another type of, material where the energy band diagram looks something like this. Again, I am taking the y-axis is the electron energy. Okay, now the energy band diagram looks something like this. So this is top of the valence band, which is EV. Now this is bottom of the conduction band, EC. Okay, and this difference, we'll call it as what? Energy gap. Yes, sir. Okay, this is nothing but what? Energy gap. So for this material, it will be approximately around 6 electron volts. Okay, approximately it is how much? 6 electron volts. We'll come to this point later. Okay, now this type of material, we usually refer it as what? What it is? It is called as insulator. Okay, it is called as what? Insulator. Okay, now Let us consider another type of material where the energy band diagram looks something like this. Okay, so this is the electron energy. Okay, now this is top of the valence band and this is bottom of the conduction band, and the difference of this is the energy gap. Again we can represent Eg is around 1 electron volt. Now this type of material usually will refer it as what? Semiconductor. Okay, usually we'll refer it as what? Semiconductor. Okay, now let us understand what this energy gap is going to represent here. So what this energy gap represents is, suppose if I can give 1 electron volt of energy to the electron which is present in the valence band, it can move into the conduction band. Okay, so if I give energy 1 electron volt, then an electron is moving from valence band to conduction band, leaving a vacancy, and usually we'll refer this one as what? Hole. Okay, how it is hole and all we'll see it later, for time being we take it. Okay, so this is what I'm giving 1 electron volt of energy. With that, the electron can move from valence band into conduction band. Now the electrons which are present in the conduction band, they are responsible for the current. Please remember. Okay, not all the electrons. We'll call these electrons, the electrons which are present in the conduction band, we usually refer them as free electrons, and they will contribute for the current. Now what about this? This is a hole. Now electron is negatively charged, this is going to be positively charged. Okay, how it is we'll see it later in detail. Okay, but you know, this is positively charged and this is also contributing for what? Current. Hope I am clear. Now coming to this insulator, here also if I can able to give 6 electron volts of energy to the electron, you can make a electron from valence band move into the conduction band, but practically the material cannot withstand this 6 electron volts of energy. Okay, so we are not in a position to modify the electrical properties of this insulator, but whereas you consider the semiconductor material, you can easily modify the electrical properties. How? We'll see it later. Okay, now in case of metal, you have only one type of charge carrier. What it is? It is the electron. Now when you come to the semiconductor material, there are two types of charged particles are current carriers. One is the electron which is negatively charged, hole. Another one is the hole which is positively charged. Hope I am clear. Okay, yes sir. Now you can give some examples for insulator. Okay, you can have the glass, okay, rubber, okay, you can have dry wood, even the pure water, but okay, pure water you can take it as what? Insulator. And coming to the semiconductor, usually we'll take what examples of semiconductor is, you can take it as germanium, silicon usually. Okay, okay, hope I am clear. So this is what, based on the energy gap, what is the parameter that we are considering here? Energy gap. We can classify the materials into these things. Now our interest is going to be in this material. What it is? Semiconductor. Okay, because if you consider either insulator or the conductor, okay, the variation in the electrical properties is going to be limited, but whereas when you consider this semiconductor, we can modify the electrical properties in different ways. We'll see how we can able to modify this. Hope I am clear with whatever the classification that I have given based on the energy gap. Okay, now if you consider suppose energy gap, if I consider the germanium material as well as silicon also, let us take germanium first. This energy gap is going to be a function of temperature. Please remember it. Okay, and this is given like this, mathematically it is given like this, 0.785 minus 2.23 into 10 power minus 4 into capital T electron volts. Okay. So what is this capital T here? It is the absolute temperature. Now, if it is a silicon material, then this energy gap is something like this. Eg of T is it? Energy gap is a function of temperature, which is given by 1.21 minus 3.6 into 10 power minus 4 into T electron volts. So what is T? Capital T is in Kelvin, which is equal to small t, which is in degree centigrade, plus 273. Yeah, you know very well this, I'm just again writing it, okay? So we can very clearly see as the temperature is increasing, okay, as temperature is increasing, the energy gap is going to what? Is going to decrease. Is it fine? So there are, many times directly the questions based on this, energy gap. Suppose if I consider, room temperature, sorry, absolute zero. Let us consider absolute zero. Suppose if you consider germanium, what is the energy gap at absolute zero? I'm putting Eg naught. Okay, what is this value? You put T equal to zero, it will be 0.785 electron volts. Similarly, if you go for silicon, then what is Eg naught? This will become, now put here T equal to 0, which will give 1.21 electron volts. Okay, I'm just putting the value into this equation. Hope I am clear. Okay, now this is at T equal to 0 Kelvin I have considered. Okay, now let us consider another temperature, nothing but room temperature you take, because usually the default temperature that we are going to consider is what? Room temperature. Okay, now for germanium, what is the value now? That is energy gap. I am calculating at 300 Kelvin. So you just put 300 here. Okay, in place of T, in place of this T, you put 300. So what is the value that I am going to get is 0.72 electron volts. And similarly, if you go for silicon and calculate this value, okay, you just put T equal to 300 here, then I am going to get 1.1 electron volts. So there are many times directly questions asked, okay, like suppose take what is the energy gap of silicon at room temperature? What it is? 1.1 electron volts. Suppose if I say the energy gap of silicon at absolute zero, it becomes what? It becomes absolute zero, 1.21 electron volts. So it is important that at what temperature you are going to consider, and almost all the parameters related to the semiconductor are going to be sensitive to temperature. Please keep it in mind. This point is very important. Almost all the parameters related to the semiconductor material or semiconductor devices are going to be sensitive to temperature. Okay, the reason is this one, the basic reason I have given. We'll see the further parameters in the later discussion. Okay, hope I am clear. Yes. Now we'll go for basic definitions that we are going to consider now. Okay, we are going to consider what? The basic definitions, because see, anything which we don't know, we feel difficult. Yes or no? Which we don't know, usually we feel difficult. But if we are practicing and practicing and practicing, once we get to know, it is going to be very easy for us. For that purpose, you need to have basic understanding. Please remember, these things are very important. If you have thorough understanding of the basics, you can deal with any type of questions that are going to be asked. Okay, now let us start by defining what is meant by electronics. Okay, with the basic definitions we'll start. Okay, I'm considering what we'll try to define what is electronics. Okay, so how you can define this electronics? So it's nothing but the branch of science and engineering which is going to deal with charged particles, or I can say motion of charged particles in a semiconductor material under the influence of electric and magnetic fields. I'll repeat again what it is. It is the branch of science and engineering which deals with motion of charged particles and in a semiconductor material. That is important. In a semiconductor material under the influence of electric and magnetic fields. Here it may be you are applying electric field separately, or separately you are applying the magnetic field, or combinedly you are going to apply electric and magnetic field. Okay, it can be anything. Okay, it is three possibilities. Hope I am clear. Okay, let me write the definition. So what it is? It is study of flow of charged particles. Okay, what it is? Study of flow of charged particles in semiconductors, under the influence of electric and magnetic fields. Okay, so here the important thing is what? Where you are dealing this? In a semiconductor material. In a semiconductor material. And here again I have already given, you may individually apply the electric field and magnetic field, or it can be a combined electric and magnetic field. Okay, hope I am clear. Okay, now what is an electronic device? Try to define this. What is? I'm defining what? Electronic device. Yeah, if you think little bit, you can easily answer these questions. Okay, so what is electronics? We have defined it is the motion of study of flow or motion of charged particles. And here, and one more thing, this charged particle means what? It can be electron or hole. Here in the semiconductor you have two types of charged particles. Okay, so that's why I generally written charged particle. It can be electron, hole. Okay, now coming to the electronic device. So how you can define? If a device is made up of semiconductor material, I can refer it as what? Electronic device. As simple as that. Okay, so any device made up of semiconductor material. Okay, so please try to concentrate. Okay, with a simple logic you can easily understand these definitions. Once you get thorough with these definitions, the other things will become easy for you. Okay, so any device made up of semiconductor material. Can you give some examples? Can I have some examples like diode, transistor, etc. Yes. Okay, so this is what electronic devices. Now we'll try to define what is an electronic circuit. What it is? An electronic circuit. So how you can define? If the circuit contains at least one electronic device, you can refer it as what? It is going to be electronic circuit. Okay, so how you can define? A circuit, okay, a circuit which contains at least one electronic device. At least one electronic device. Is it fine? Okay, can you give the examples for this? Can I have some examples like rectifier, yes or no, oscillator, okay, and amplifier, etc. Am I correct? Okay, So how you can define electronic circuit? A circuit which contains at least one electronic device, you can refer it as electronic circuit. Okay. Now in the similar way, we can define what is an electrical circuit. What is an electrical circuit? Yeah, hope you know all these things, but I'm just refreshing the things. Okay, try to concentrate. Okay, so how you can define? If the circuit contains RLC components, that is resistance, inductance, and capacitance. Okay, a circuit which contains a circuit which contains RLC components. Okay, then you can refer it as what? Electrical circuit. Okay, now you consider either electronic device or electrical device. We can categorize into two. One is called the passive device, the other one is called as active device. Okay, so let me write that point. All electrical and electronic devices can be categorized into one is passive, okay, passive device, and the other one is what? Active device. Hope I am clear. All the electrical and electronic devices can be categorized or classified into what? A passive device and an active device. Okay, now let us consider one by one what is this active and passive devices. Okay, let us take first the passive device. Okay, I'm considering what? Passive device. Yeah, how you can define this passive device? Yes, the one way I can define it is a device which can dissipate energy. Okay, let's try to understand. One way of defining is what? A device which can dissipate energy. Yes or no? So can I have the example for this? A device which can dissipate energy. What it is? It is nothing but the example is resistor. Yes. Now another possibility is a device which can store the energy, then also you can call it as what? A passive device. Yeah, can you give the examples for this? You can have inductor and capacitor. Yes sir. So we know that this is going to, inductor is going to store the energy in the form of what? In the form of what? Current. Yes or no? In the form of current in where? Magnetic field. Yeah, these are basic which we know. Yes or no? Inductor is going to store the energy in magnetic field in the form of current. Then what about capacitor? It stores the energy, okay, in the form of what? Voltage, okay, in electric field. Am I correct? Yes. A device which can store the energy we are defining. How? It can be an inductor or it can be a capacitor. Now, inductor is going to store the energy in magnetic field in the form of current, whereas capacitor is going to store the energy in electric field in the form of voltage. Yeah, these things we know very well. Yes or no? Okay. Now let us go for passive device. Sorry, passive device we have completed. Let us go for the active device. Okay. Let us consider active device. Yeah, this also we can have in different ways. Okay, the first possibility is, okay, a device which can act as source of energy. You can refer it as active device. Okay, let me write that. A device which can, yes, a device which can act as source of energy. What? Source of energy. Then I can call it as what? I can call it as what? Active device. Okay. So can you give the examples for this? Yes. Can you give the examples? All the voltage and current sources. Hope I am clear. A device which can act as source of energy can be referred as what? Active device. Can you give the examples? All the voltage and current sources. These are independent, please remember, okay? Independent voltage and current sources. Now, the other possibility is, okay, other possibility is a device which can perform, yeah, please, these definitions are important, okay? That is the reason why I'm spending time here, okay? So please, again, I'm mentioning one important point here. Whatever I'm teaching here is going to be required for you. Please take it for granted. See, finally, I want to make you to, perform well in the examination. That is the objective. Okay, let us have better understanding. Whatever your motive and my motive is, same, then there will be, harmony in what we are discussing. Okay, so whatever I am discussing here, this is essential for you. Don't have second thought in your mind. Okay, so write the exam, and anyhow we'll give the mail IDs and all. If you really don't, any topic that is not required, okay, you can just intimate me. Okay, so please, again, I'm requesting you, please concentrate and take it for granted. Whatever I'm teaching here is required for you. Fine. Okay, now the second way of defining this is a device which can able to perform amplification. Okay, a device which can perform what? Amplification. Okay, so in that case also you can call that particular device as what? Active device. Yeah, can you give some examples for this? Yes. So usually all the transistors can able to perform the amplification. Okay, so I can have all the transistors. Hope I am clear. All the transistors. Now there is other possibility of defining this. A device which can perform switching. Okay, yes or no? A device which can able to perform switching. In that case also you can call the particular device as what? An active device. Okay, now can you give the examples here? Yes, a device which can able to perform the switching. Anyhow, transistor, you can use it as a switch. So I can write transistor. Any other examples? Yes, you have silicon control rectifier, no, SCR, specifically used for the switching, okay, etc. Hope I am clear. Yes, sir. So let us consider again, passive device. How we have defined the passive device? A device which can dissipate the energy. Example, we have given it as the resistor. Okay. Then a device which can store the energy. Then what about the examples we have given, inductor and capacitor. Then coming to the active device, a device which can act as a source of energy for the external world, you can refer it as what? Active device. The examples we have given all the voltage and current sources, independent. Okay. Then coming to the second way of defining it, a device which can able to perform the amplification. In that case, all the transistors can be taken. And in the third way of defining it is a device which can able to perform the switching. And examples again, transistor can be used as a switch, and one more we have taken it as the SCR. Okay. Now, my dear students, I have a doubt here. Okay. Let me ask that doubt. Try to get the answer on your own. Anyhow, I am going to explain. Okay. Suppose you take the diode. Okay. I am considering what? Diode. Okay. Diode. Now, this diode is normal PN junction diode I am considering. Okay. Is this PN junction diode is an active device or passive device? Is my question clear? I am considering ordinary PN junction diode. Now, whether this PN junction diode is an active device or passive device, that is what my question is. Okay. Whether it is active or passive device. Yes. Is it active or passive device? It's going to be passive device. But according to the definition that we have given, a device which can perform switching, okay, you can take it as what? Active device. But anyhow, you can use the diode as a switch. Yes or no? But still it is not an active device, it is a passive device. Okay, so what is the reason? Please try to concentrate. Suppose you take a particular device. Okay, there should be 3 terminals minimum. Okay, now I have one input terminal, one output, and one is going to be the control element. Okay, so this is input, this is output, and this is the control terminal. This is called what? Control terminal. Okay, then based on this you are switching. Okay, you are switching. Okay, and this is going to control the flow of signal from input to output. Okay, then I can call it as what? Active device. Even though diode can able to perform the switching, it is not having third terminal, which is called as the control terminal. It has only 2 terminals. So you are not supposed to refer this diode, normal PN junction diode, as the active, even though it can able to perform the switching. Okay, so please try to understand this. Okay, so any device which is having 3 terminals, one is the input terminal, okay, and the other one is the output terminal, and what about the third one? Control terminal. Then you can refer it as active. Okay, but in case of diode, if you consider, okay, if you take the diode, so how the circuit symbol you can represent for the diode? Like this. This is P and this is N region and this is a junction. So you can very clearly see there are only 2 terminals. So even though you can use it as a switch, it is passive device. Please remember this. Okay, please try to understand. Okay, don't try to by heart, try to understand. Okay, if you understand the basic definitions, you can easily remember this. Okay, that is the reason why I'm going step by step. Okay, so it is the passive device. Now suppose you consider a tunnel diode. Okay, what it is? Consider a tunnel diode. Now tell me whether this is active or passive device. Yes, tunnel diode is active or passive? It is going to be active device. What it is? It is going to be active device, not passive. So here still the tunnel diode is going to have what? two terminals. What is the circuit symbol for tunnel diode? Like this. Yes or no? So still it has the two terminals, but we can call it, we can take it as what? Active device. The reason is there will be a negative resistance region in the VI characteristics. So in any device VI characteristics, negative resistance region is present, then you can refer that particular device as active device. Okay, there is no constraint for this, three terminals or two terminals. Hope I am clear. Let me write that point. If negative resistance region is present in the VI characteristics of any device, then it is referred as what? Is referred as active device. It is referred as what? Active device. Please try to understand this. According to the definition that we have given, the third definition, if you take a device which can able to perform switching, we may think that diode is going to be, this is ordinary PN junction diode. Diode is going to be active, but it is not active, it is passive. The reason is this one. Okay, so there should be a control element, okay, which is going to control the flow of signal from input to output. Then it can be referred as what? Active device. If it can able to perform the switching, and it can be referred as active. But if you take the diode, I have only two terminals. Now if you go for that one example I have taken, you can have gun diode also. Okay, so tunnel diode if you take, so it is going to be active. What is the reason? There is a negative resistance region in the VI characteristics. Then you can refer it as what? Active device. Okay, hope I am clear. Yes or no? So this is how we can classify the devices, active and passive devices. Okay, now let us consider another way of classifying the electronic circuits. Okay, so I'm classifying what? Electronic circuits. Okay, so there are three ways of three different categories. One, we can call it as analog circuits. What it is? Analog circuits. The second one is digital circuits. Okay, hope I am clear. One is the analog, another one is the digital, and the third category is mixed signal. Okay, mixed signal. So if you understand or clearly observe the name, you can get it what it is. Okay, so what is this analog circuit? If both input and output signals are analog in nature, then you can call it as what? Analog circuit. Yeah, can you give some examples for this? Yes, you can have the amplifier. Yes or no? Amplifier, oscillator, etc. Yes. Okay, now in a similar way, how you can define digital circuit? If both input and output signals are digital in nature, you can call it as a digital circuit. Okay, so if both input and output signals are digital in nature, or digital in nature, then you can refer it as what? Digital circuit. Now, what are the examples that you can give? You can give the shift register, listen, shift register, encoder, decoder, listen, mux, that is multiplexer, demultiplexer, etc. Okay, hope I am clear. Now coming to the mixed signal, the name itself is giving one is going to be analog in nature, the other signal is going to be digital in nature. Then you can call it as what? Mixed signal. Yes, input output signals, one will be digital, one will be analog. So what are the examples? Now very well, it is ADC, analog to digital converters, and digital to analog converters. Okay. Now, if you go for your masters and all, you can have specializations. You can choose the analog circuit design, digital circuit, and mixed signal as take for your masters and PhD. Then you can choose these things. If you consider the difficulty level of designing these circuits, which is going to be easier one out of these three? Digital circuits. Then comes the next difficult level is going to be analog, and mixed signal is going to be the most difficult or complicated one. What is the reason is, what is digital, you are going to represent with 0 and 1. Yes or no? For a certain duration, your output can be 0, and for certain duration, your output is 1. So you are allowing your device to settle down for certain time. So that's why it's going to be easy. But what about analog? Continuously the amplitude is changing, input amplitude or input signal changing. According to that, the output signal also has to change. In that way, you have to design the circuit. Yes or no? Okay, so that is the reason why compared to the analog and digital circuit, digital is going to be easier than the analog, because 0 and 1, for certain duration it is 0, and for certain duration it is 1. But analog, it is not the case. Continuously the input signal is changing. According to that, the output has to change. Okay, and you can see mixed signal, one is analog, the another one is the digital. It is going to be much more complicated. Okay, so you can you can find you can count the people who are expertise in analog I am talking analog circuits, okay, on fingers. Okay, so this is going to be very if you are really interested, you can choose this analog circuits. It's going to be a very good challenging task for you. Okay, and very interesting also. Okay, hope I am clear. So how we can classify these electronic circuits. Okay, now let us consider another way of classifying. These are some examples I am giving. Okay, please concentrate. Okay, so I am considering now device classification based on different parameters. Now I am considering what? Device classification, okay, based on different parameters. Okay, we'll see one by one. The one way I'm classifying is based on the amplitude of the signals that we are going to consider. I can call it as small signal or what? Large signal. Small signal or large signal. The large signal is also called as what? Yes, large signal is also called as what? Power devices. Yes or no? It is also called as what? Power. Okay, power devices. Okay, so what is the reference? Sorry, what is the reference I am taking here? The amplitude of the signal. Okay, so we know what is the operating point. Around this operating point, if the signal variation is very small, then you can call it as small signal. I'll repeat. You know what is the operating point? You are fixing any device you consider, any circuit, you have the operating point. So around this operating point, the variation of the amplitude is going to be very small. Okay, then you will call it as what? Small signal. If it is very large compared to that, then it is going to be large signal or power device. I'm just giving the few devices only, not the complete list. Okay. Now another parameter, let us consider the frequency. Then I can call it as what? Low frequency and high frequency devices. Low frequency and high frequency devices. Okay. So when you go for device, design, okay, or construction under low frequencies and high frequencies is going to be different. It's going to behave differently. Okay, so this is one more classification. Okay, then I can have discrete devices, discrete and IC devices. What is IC? It is integrated circuit. Discrete is only one component I have, whereas integrated circuit, what is integrated circuit? On a single chip, you have millions and billions of transistors. Yes or no? That is what? Okay, we are fabricating the many number of transistors on a single chip. Then it is integrated. Okay. Again, behavior may change from discrete to integrated circuits also. Hope I am clear. Now you can have micro electromechanical systems. What is this? MEMS is micro electromechanical systems. Mechanical systems. MEMS. Okay. Then another one is you can have, instead of micro, you can have nano also, NEMS. You just replace this micro with nano. It is nano electromechanical systems. Okay, hope I am clear. Then you can have optoelectronic devices. What it is? Optoelectronic devices. The name itself is indicating here opto and electronic. Okay, so that is, it is going to convert light energy to electrical energy to light, and that is what opto. Anyhow, this we are going to consider. Okay, in our syllabus we need to discuss about optoelectronic devices. Now if you consider the last three that we have indicated here, you can very clearly see you are converting one form of energy into another form. Yes or no? You are converting, that is conversion of one form of energy into another form. Yes or no? So usually what these devices are referred as? Transducers. Yes or no? Transducers. Hope I am clear. So this is another way of classifying it. Okay, but this is not the complete list of devices. I have given few examples to make you to understand what is the importance of semiconductor material or the other devices is going to be. Is it fine? Okay. Now, okay. So hope I am clear with whatever I have given now, the basic definitions. Okay, you must understand. Okay. Now let us consider one important thing here. Okay, if you consider a system in electrical engineering, there will be two systems broadly. And why I'm going for semiconductor devices? This is very important. You must understand what is the importance. Why can't be other devices? Why you are using only semiconductor devices? You must understand. Okay. Now what I'm considering is, you consider systems in electrical engineering. Okay, yeah, electrical or electronics, you can have it. Okay, systems in electrical engineering. So broadly you can have two things. Okay, two systems you are going to have. One is called as energy system. Yeah, please try to concentrate. This is very important so that you can appreciate what is the importance of the semiconductor materials or devices. Okay, one is what? Energy system. The other one is called information system. The other one is what? information system. Okay. Now we'll try to understand what this energy system will do and what this information system is going to. So the name itself is indicating energy system is going to do what? It is going to generate, it is going to distribute, and it is going to regulate the energy. Okay, so let me write that. It generates, distributes, and what? Regulates the energy. Okay, there will be some subsystems that are going to be present. So it is going to generate, distribute, and regulate the energy. Now, what about information system? Yes, so it is going to store the information. It has to process the information. It has to communicate with the other systems that are going to be present. Okay, let me write that. What it is? Store, process, and communicate information. Hope I am clear. Yes, energy system, information system. What energy system will do? It generates, distributes, and regulates the energy, whereas information system store, process, and communicate the information. Fine. Now, where your semiconductor materials are going to play the important role is the semiconductor devices. Okay, the semiconductor devices enhances. Okay, there are different parameters. Enhances, first one, enhances performance. Okay, performance. Then what about? It should be reliable also. Yes, sir. It is not only performing well. It should be reliable. Okay, performance, reliability. Okay, and not only that, it should be cost effective. Yes, sir. Cost should be low. Okay, and cost effectiveness of energy and information system. Energy and information systems. So this is the importance of the semiconductor material. So what it is doing? It is going to enhance the performance, reliability, as well as the cost effectiveness of both the energy system and the information system. Okay, and this is the reason why we are choosing the semiconductor devices. Okay, so these are any system you consider, these three are very important. Yes or no? These three are very important. Okay, so for semiconductor material, I can able to get all these three parameters using the semiconductor materials or devices, and that is the reason why we are going for what? Semiconductor devices. Hope I am clear. Now let us give another broad perspective of what we are going to discuss in our subject. Okay, now the first one that we are going to understand is going to be called as terminal characteristics. What it is? Terminal characteristics. Sorry, terminal characteristics. So you see any device, we need to get the terminal characteristics. Okay, and what are the different terminal characteristics that we must obtain? Yeah, if you know, just think, you can get the answer. What type of signals you are applying here? Either you are going to apply the DC signal or AC signal. So obviously terminal characteristics means I should get the DC characteristics, and another one is AC. In case of AC, there are two things. One is the transient response. The other one is the steady state response. Yes. Okay. So under terminal characteristics, what you can write? It is DC current voltage characteristics. Yeah, usually DC quantities we are going to represent with the capital letters. I am following the same. Okay. Then what about AC? I have AC, no, transient response. AC transient characteristics. So usually I'll refer it with what? I of t, V of t. I of t, V of t. Is it fine? Transient. Now similarly, what is the other possibility? AC steady state. AC steady state. And this is also called as what? Small signal characteristics. Yeah, you need to understand this terminology, okay? AC steady state is also called as what? Small signal analysis or small signal characteristics. Now here, I am going to represent like this only. Why? See, what is the difference? The second AC transient, still it is dependent on the time, transient response. But what about steady state? It is already reached the steady state. Now it is not dependent on the time. That's why I'm writing simply IV. It has been reached the steady state. Okay. Now, in our analysis, anyhow, we'll discuss about DC characteristics we need to consider. Okay. And we are going to consider AC steady state or what? Small signal. Okay. So we are not, considering with the transient unless it is mentioned explicitly. Default in AC analysis, we are going to deal with what? Steady state analysis. Please keep it in mind. Okay. Hope I am clear. Now let us go for the other one, which we are calling it as material parameters we need to consider, because the devices are going to be made up of what? Semiconductor material. So whatever the characteristics that we are having for the material, it decides the device characteristics. Okay, so I need to have material parameters. We must understand material parameters. Now under this, what are the different parameters that I can list? Yes, starting with, just now we have discussed at the beginning, one parameter we have taken it as what? Energy gap. Can I write it? Energy gap. Yes. Hope I am clear. Then what is the other one? Can I have the dielectric constant, basic material parameter? Yes or no? It is dielectric constant. Yes or no? Then mobility, very important parameter. Okay, mobility. Then in the semiconductor material, if you want to make the extrinsic semiconductor material, how we are going to do that? By doping. So I should have the doping here. Yes or no? Energy gap, basic parameter, dielectric constant, mobility, doping. Then once you dope this, okay, there is one parameter called as lifetime. Okay, that is, please remember one important point. In the semiconductor material, if the temperature is more than 0 Kelvin, there will be always generation and recombination of electron hole pairs. I'll repeat this point. Once the temperature is more than 0 Kelvin, in semiconductor material, whatever it may be, intrinsic or extrinsic semiconductor material, always there is generation and recombination of electron hole pairs. So that from that we can give this. Okay, what is it? Lifetime. This is another important parameter. And anyhow, the geometry of the device. Okay, geometry of the device. So these are the different material parameters that we can consider. But it is energy gap, dielectric constant, mobility, doping, lifetime, and the geometry. Okay, and another one which we need to understand here is the ambient conditions. What it is? Ambient conditions. So this is also very important one. Okay, and we need to relate these three. We'll see how we can relate them. Now, what is the ambient condition? We can have default, it is temperature. Yes or no? default. Okay. Ambient condition is what? Surrounding, suppose if this is an electronic device, surrounding this there is an environment and it has the certain temperature. And this also decides the characteristics now. Okay. And we have very clearly mentioned that any electronic device or semiconductor device is sensitive to temperature. Please keep it in mind. Okay. Now another one is the illumination. What is that? Illumination. So what is meant by illumination? You are sorry, what is illumination? You are making the light energy to fall on the semiconductor material. It will absorb the light energy and it generates electron hole pairs. That is what illumination is. Hope I am clear. So we have terminal characteristics, material parameters, ambient conditions. Now whenever you change the any one of material parameters or ambient conditions, we can very clearly see that the terminal characteristics are going to be get affected. Am I correct? Okay, let me write that. If you consider the material parameters, and the ambient conditions, so if you change these things, then this is going to change what? What it is going to change? The terminal characteristics. Yes, terminal characteristics are going to be affected. Please try to understand this point. This is very important one, because this is what we are going to do throughout our subject. If we change the material parameters or ambient conditions, there is a change in the terminal characteristics. Or suppose if I have certain terminal characteristics, if I give, then by modifying the material parameters or ambient conditions, I can get it anyway. Two way it is possible. Yes. See, I can give the certain material parameters and ambient conditions. From that we can analyze what is the terminal characteristics. Or I want these type of terminal characteristics I am mentioning. Then by modifying the material parameters or ambient conditions, I can get the specific terminal characteristics. Okay. Please, whatever we are going to consider now. Okay. Whatever we are discussing as a whole. Okay. As a broad perspective, I am giving here. And this is what we are going to do. Either it is a diode transistor or field effect transistor. This is what any one of these things that we are going to consider it. Okay. So hope I am clear with what I am explaining. Please, again I am mentioning, please, you may have certain way of, you have practiced or you have adapted certain way of learning the things. Now there will be a little change or little deviation from that. You may feel difficult initially, but I am promising you, okay, once you get adapt to this, whatever I am teaching, the things will become easy for you. But you need to listen with concentration and you have to practice. You have to ensure it. Okay. If these two things are there, I'll guarantee that you are going to get the good gate rank. There is no doubt about it. Okay. Clear, students? Now we'll go for another very interesting and very important topic that you must understand. Why I am choosing the semiconductor only? Why not be other? Okay. So if you want to appreciate that, we must understand the different properties of the semiconductor. Okay. Let us consider that. Okay. So what I am going to consider here, properties of semiconductors or semiconductor. Okay. So what I am considering, properties of semiconductor. I'm sorry. Now, yeah, what could be the just think, you just use your common sense. You can easily list these different properties. Why basically we are going either you can consider the conductor or semiconductor. What is the basic property? Charged particles. Yes or no? Obviously, charged particles. And later on different things will come. How many number of charges are present and there, we can list it. So basically what I can have properties under the first one. Yes. If you consider the conductor, I have already mentioned one important point that I have only one type of charge carrier. What is that? In a conductor, what it is? Electron, which is negatively charged. What about semiconductor? You have two types of charge carriers. So can I write polarity of charge carriers? What it is? Polarity of charge carriers. Am I correct? Now, once you know this, anyhow, we know, we'll discuss one by one. Okay, let me first list out the different properties. Then what is the next parameter that is going to decide for your electrical properties? How many number of charges are going to be present? Am I correct? Okay, so can I say concentration of charge carriers? Yes, sir. What it is? Concentration of charge carriers. Please try to understand logically. I am putting one by one. Okay, polarity of charge carriers. Then what it is? Concentration of charge carriers. Yeah. Then what could be the third one? How you are making these charges to move from one place to the other place. Yes, sir. Okay. So can I say transport of charge carriers? What it is? Transport of charge carriers. So hope I am clear with what I am explaining. Okay, logically I am writing one by one. Polarity of charge carrier, then comes how many number of charge carriers are present, nothing but concentration of charge carriers. Then what is the third one? How you are making these charges to move from one place to the other place in the semiconductor material or device, nothing but what? Transport of charge carriers. Fine. Now, what about the next property that I can list? So if you remember the definition that we have given for the electronics, what it is? It is the study of flow of charged particles in a semiconductor under the influence of electric and magnetic fields. Now, these charged particles are going to interact with the electromagnetic field. No? So can I say interaction with electromagnetic field? Yes, what it is? Interaction with interaction with electromagnetic field, nothing but EM. EM is what? Electromagnetic field. Hope I am clear. Okay, so these are the four important properties that we must understand to appreciate the importance of the semiconductor materials. Fine. Yeah, now let us consider one by one these four properties. Okay, briefly we'll discuss. Okay, and then we'll go for the next topic. Okay, please, you need to understand these 4 points that we are going to discuss to appreciate the semiconductor materials. Okay, please concentrate. Sorry. Now we know very clearly that what could be the polarity of charge carriers. I have two types of charge carriers. One is the electron, which is negatively charged, and what about the other type of charged particle, which is the hole, and it is positively charged. Yeah, we'll understand how it is positively charged later. Okay, for time being you take it. Okay, so polarity of charge carriers is what? There are two types of charge carriers. One is the electron, which is negatively charged. The another charged particle is hole, which is positively charged. Okay, now let us consider the second property we'll consider here. Okay, what it is? Concentration of the charge carriers. Okay, so please try to understand this. Now here I am taking, okay, so this is carrier concentration. I am taking what it is? Carrier concentration. Okay, now suppose if this carrier concentration is 10 power 6 per centimeter cube and less, okay, one boundary we are defining, then this type of material usually we'll refer it as insulator. Please try to understand this. Okay, if the carrier concentration is less than 10 power 6 per centimeter cube. Per centimeter cube I am taking, that is unit volume. Then usually you will refer it as what? Insulator. Now another boundary we can give, another boundary value is 10 power 21 per centimeter cube and above, then this is referred as conductor, okay, or what is the other name that we can give? Metal. Okay, now if the carrier concentration is in between these two values, okay, that is 10 power 6 to 10 power 21 per centimeter cube, you can refer this type of material as what? Semiconductor. Okay, so the important point that you must understand here is, okay, see, you can vary the carrier concentration from 10 power 6 per centimeter cube to 10 power 21 per centimeter cube, which is almost 15 orders of magnitude. Sorry, 15 orders of magnitude you can change the carrier concentration. Okay, so how you can change this carrier concentration? One way is you can dope the semiconductor material. Yes sir, you can dope. One is the doping, one method. Another one is illumination. Okay, even with the temperature you can modify. If you change the temperature, that also changes the carrier concentration. So these are the few examples that I have given how we can modify the carrier concentration in a semiconductor material. We know very well doping and illumination. Also with the temperature it is going to change. Is this point clear? This is very important one. The second one, concentration of charge carriers, you must understand that the important point you can very clearly see from this, there is 15 orders of magnitude you can change the carrier concentration. Sorry, that is from 10 power 6 per centimeter cube to 10 power 21 per centimeter cube, 15 orders of magnitude. This is the very important property where this is not possible in case of metal and insulator. It is not possible. Okay, but here in the semiconductor material there is a large variation where in the carrier concentration you get, and how you can get? Either you can dope the semiconductor or you can illuminate the semiconductor material. Even with the temperature also you can increase the carrier increase or change the carrier concentration. Hope I am clear. Okay, now let us go for third property. What is the third property that we have listed? It is the transport of charge carriers. What it is? Transport of charge carriers. Okay, we'll see one by one here also. Okay, yeah, how you can make the charges to move from one place to the other place? We know very well one type of transportation, we'll call it as the drift transport, or you can call it as the drift current. Yes, we know very well what is this drift. So how you are making the charges to drift from one place to the other place? By creating the potential gradient. Okay, why I am getting drift? You are creating the potential gradient. Okay, because of that there is an electric field that is going to be developed. Hope I am clear. Okay, so let me write the reason for that. Why I am getting this? Due to what? Potential gradient. Okay, so that is the charges will move from higher energy to lower energy, or higher potential to lower potential. Yes or no? So this process is called as what? Drift. So you can observe this drift in the metal or conductor. We know this. Okay, now there is another possibility which we will call it as diffusion. Okay, what it is? Diffusion. So why I am getting this diffusion? This is going to be because of what? Because of concentration gradient. concentration sorry, due to what? Concentration gradient. So what is meant by gradient with respect to, distance? Some parameter is changing. That is what gradient. So here, what is changing? Concentration. In the case of drift, it is potential. Now, this diffusion, where you can observe this diffusion in case of semiconductors, but this is not significant in case of the metal or conductor. Okay. Now, there is another, possibility of getting the current or the transport, which we usually call it as thermoelectric current. What it is? Thermoelectric current. Okay, thermoelectric current. Yeah, this is drift current, diffusion current, thermoelectric current. Or drift transport, diffusion transport. Another one is due to thermoelectric effect. Okay. Yeah. Why I'm getting this? Why I'm getting this thermoelectric? The name itself is indicating there is a temperature gradient. Okay, so it is due to temperature gradient. Hope I am clear. Okay, so drift, diffusion, thermoelectric current. These are the three different transport mechanisms that are possible. Okay, why we are getting drift? By creating the due to the potential gradient. Diffusion because of concentration gradient. Thermoelectric current is because of what? Temperature gradient. So the important point that you must understand here is okay, the second one and third one, that is diffusion and thermoelectric currents, are going to be significant, okay, in case of semiconductor, and they are insignificant in case of conductor. Okay, hope I am clear. They are not significant in the metal, but they are very important mechanisms in case of what? In case of semiconductor material. Okay, so this you must understand. Okay, so let me write that point. Thermoelectric and diffusion currents, okay, are not significant, in case of conductor. Okay, they are unique properties of semiconductor. So again, you can see, the important property of the semiconductor. Okay, so again, one more reason why we are considering the semiconductor material. Okay, so this diffusion and thermoelectric currents are not significant in case of metal, but they are going to be the unique properties of what? Semiconductor materials. So hope I am clear. Yes, now we'll go for the third type of property. What it is? Sorry, fourth one. It is interaction with the electromagnetic field. So please try to understand this. Whatever we are going to discuss in this fourth property in detail, we are going to consider optoelectronic devices. Okay, so let me write the heading first. So what we are going to consider here: interaction with EM field, electromagnetic field. I'm sorry, one second. Okay, so what we are considering now: interaction with the electromagnetic field. Okay, now let us consider, you are illuminating the semiconductor material. Let us take this is the atom. Okay, a particular atom I am considering here. Okay, now you are making the light energy to fall. Let us take this is h nu, the photon energy. Okay, what is the condition here? It should be at least energy gap. So h nu is greater than or equal to Eg. Then only this photon is absorbed by the material, and what will happen once it is absorbed? It can generate the electron hole pair. Please try to concentrate. Electron hole pair. So usually we'll refer electron hole pair like this EHP. Please remember this, okay? This notation. What it is? EHP. What it represent? Electron hole pair. So by absorbing the light energy, okay, the material is producing electron hole pair. What is the meaning of this generation of electron hole pair? You are placing the electron from valence band into conduction band. Now the electron which is present in the conduction band becomes a free electron. There is a vacancy that we are calling it as hole. Hope I am clear? Okay. Now we can very clearly see by absorbing this light energy, the carrier concentration is changing. No, electron hole pair. These are the free carriers now. These are responsible for the current now. Yes. So by absorbing the light energy, you are modulating what? Conductivity of the material. So this effect, we can call it as what? Photoconductive effect. What it is? Photoconductive effect. Okay. So if you consider the light dependent resistor, okay, LDR, this works on the principle of this, yes or no? By sorry, if the light intensity is changing, the resistance is going to change. Okay, and there is one more device that we can consider called as the photodiode. What it is? Photodiode. So this also works on the principle of what? What? Photoconductive effect. So it is nothing but what? Light energy is falling on the diode. It will convert that light energy into electrical energy, nothing but the current. Okay, so you can call it as optical detector. Anyhow, this photodiode we'll discuss in detail later. I'm giving some examples. Now the same thing from the same by considering this, we can have photovoltaic effect with little modification. What it is? Photovoltaic effect we can get. Okay, so what is the any device that which is working with the photovoltaic effect? Nothing but solar cell. What it is? Sorry, solar cell. Anyhow, we are going to again discuss the solar cell in detail later. Hope I am clear. This is one way of interacting the light energy or the charges with the electromagnetic field. Hope I am clear. Now the important point, I have already mentioned this, again I am mentioning, if T is greater than 0 Kelvin, okay, T is greater than 0 Kelvin, always there is generation and recombination of electron hole pairs. Please keep it in mind. G, capital G represents here what? Generation. Capital R is the recombination of what? Electron hole pairs. But either it is an intrinsic or extrinsic semiconductor material. Now, once you have generated this electron hole pair, see this electron, whatever you are exciting into the conduction band, it is the excited state. It is not the equilibrium state. Yes or no? Okay, so it has to come back at certain time. After a certain time, it will come back to its valence band. I'm sorry, but may not be into the same location, but definitely it will come back to valence band. Now when it is coming from conduction band to valence band, what will happen? There is a difference of energy, no, in certain type of materials, not all type of materials. Okay, in certain type of materials, the difference of energy will be released as the light energy. Okay, now whatever the electron hole pairs that are generated, they are recombining now. Okay, this is electron and this is the hole, they are recombining. Now when they recombine, that energy difference can be released as the photon H nu. Okay, hope I am clear. And please remember, this will not happen. The light energy may not be observed in the all type of materials. We also consider this later. Okay, in case of direct band gap semiconductors only this can happen, but not in indirect band gap semiconductors. Okay, yeah. Anyhow, we'll discuss that also. Okay, fine. I'm clear with what I have written now. Now, if the process, in any process you consider that the output is going to be the light energy, then we will call it as the luminescence. Okay, if the output is the light energy, then we'll call it as what? Luminescence. So this process we'll call it as, or we'll refer it as what? Electroluminescence. This is called as what? Electroluminescence. Okay, now we'll try to understand what is this luminescence. Refers, output is light energy. Please understand, light energy. Okay, and what this electro refers? Input is electrical energy. Okay. So this is called as what? Electroluminescence. Please remember, default, if the output is light energy, we'll refer that as what? Luminescence. Here the input is what? Electrical energy. That's why it is what? Electroluminescence. So any example you can give for this? Any example? Yes, you can have light emitting diode, laser. Okay, light emitting diode and laser. Yes. Now there is another possibility. Now whatever suppose you consider you are illuminating the semiconductor. This is the atom. You are making the light energy to fall, H nu, which is H nu 1 you take, which is greater than or equal to energy gap. Now this produces or generates electron hole pair. Now again they are going to recombine. Okay, now in this process again we can observe the light energy, but the energy of the photon is different now, H nu 2, because there will be some some of the energy will be wasted in the material and H nu 2, and usually you can have nu 2, okay, will be less than u1. Obviously energy of the output photon will be less than this. Now this process again we are getting the output as what? Light energy. You can call it as what? Luminescence. And what is the input energy here? It is the light. So this process usually refer it as photoluminescence. What it is? It is referred as photoluminescence. Okay. So again, what is the meaning of this luminescence? Yes, output is light energy. And what about this photo refers here? Input is light energy. Okay, yeah, you can search on your own what are the different examples for this. Okay, you can search the practical applications of photoluminescence in the web. You can get some examples for this. Hope I am clear. Yes. So interaction with the electromagnetic field. Okay. So when you illuminate the semiconductor material here, it is absorbing the light energy which releases electron hole pair. And because of that, the conductivity is going to get modulated, and we are calling it as what? That effect, photoconductive effect. And we are given the example for such type of devices is LDR, and another one is photodiode. And with a little modification from this, we can get another effect called as photovoltaic effect. And what are the examples? Solar cell we have given. Fine. Now the excited electron, again it will come back to its valence band. In that process, in certain type of materials called as direct band gap semiconductor materials, you can observe the output as the light energy. Now whenever the output is the light energy, you can call that process as what? luminescence. Now, what is the input here? Electrical. That's why it is called as electroluminescence. Okay. Now, another possibility is photoluminescence. So here you are giving h nu 1 as the energy for the input. Now electron hole pair has been generated. Again it is recombining where I can again observe the light energy. Now this energy is going to be definitely less than this original, and that is the reason why I am writing nu 2 is less than nu 1. What is this process is called? Photoluminescence. Okay. And examples, please go through your, you just type the practical applications of photoluminescence. You can get some examples and try to understand. Okay. But anyhow, this photodiode, solar cell, LED and laser, later we are going to consider and we'll discuss in detail. Okay. So hope I am clear with whatever the explanation that I have given. Okay. So this is these are the very important, properties or, characteristics that you must understand of semiconductor so that you can appreciate the importance of the semiconductor material. Okay. So specifically, please try to understand whatever we have given, properties of the semiconductor, the 4 different properties. Try to understand these things. Okay. And whatever the further discussion that we are going to make in the semiconductor and further the devices, these are the 4 that we are going to consider. Okay, so these are the 4 broadly. Okay, and in the device characteristics, these are the broad way that I have given. Any device you consider, you have to get the terminal characteristics, and these terminal characteristic depends on what? Material parameters and the ambient conditions that what we have given. Okay, so hope I am clear with whatever I have given now. So if you have any doubts, you can raise. Okay, we'll take up doubts for another 15 minutes and then we'll take a break. Okay. Yeah, doubts and none. Doubts on the thesis break. Yeah, please, when you are asking a doubt, okay, please be careful, okay, because most of the times 50% of the doubts, okay, which you are going to get, okay, they can be clarified by on your own when you read that particular topic for the second or third time. Okay, and few doubts you can discuss with your friends and get clarified. Okay, I think only for very few questions, maybe 5 to 10%, you require the teacher. Okay, so please, the questions that you are going to ask, Okay, so please think and ask the questions. Okay. Anyhow, I'll definitely clarify. There is no doubt about it. Okay, but try to understand. Okay, I need to answer so many questions. No. Okay, so few questions you can get it on your own. Okay. Yeah, if any significant doubt is there, I'll answer. So can you please explain? Yeah, it is electron hole pair. EHP I have very clearly mentioned. No, EHP means electron hole pair. Okay. What is electron hole pair? When you are making the electron to move from valence band to conduction band, okay, there is a corresponding electron and hole. That is what we are calling it as electron hole pair. Okay, EHP. In short form, we'll write it. Okay. Yeah. Regarding the reference textbooks, okay, I'll give it to you at the end of the course, because if you try to understand whatever I'm explaining initially, okay, because I'm referring so many textbooks and making your concept very simple for you, and then you can go for the reference books. Don't worry, I'll give the reference textbooks. Okay, what are the different reference textbooks for us? Okay, please. Yeah, component and device, component is the what it is. Component and device interchangeably you can use it. Component is one part of your element circuit, and anyhow device is also one part. Component you can call it. It's not a much deal. Okay. Yeah, someone asked, is Zener diode is active or passive? Please try to check on your own. We have very clearly mentioned, you know what is active and what are passive devices. Check on your own. Okay. Yeah, someone asked, can you explain the fourth property? Yeah, I'll go through it once again later. Okay. Yeah. Yeah, content I'll discuss. Okay. And someone asked, what is the meaning of photovoltaic? Please, again, I have very clearly mentioned these devices we are going to discuss in detail later. For your understanding purpose, I'm giving here. Okay. Try to cope up with that. Okay. Yeah, someone asked, yeah, conductor insulator, it's not the same, no, because your EC and EV are different. No, here this is EC, this is EV. There is an overlap in the between conduction band and valence band, but in case of semiconductor there is an energy gap. Please try to understand this. Okay, this is EC, this is EV. Here it is, this is EC, this is EV. Okay. Yeah, someone is asking photoconductive effect. So here what you are doing, by absorbing the light energy, by absorbing the light energy, what is happening? Electron hole pairs are generated. Now once the electron hole pairs are generated, there is an increase in the carrier concentration, which you are modulating the conductivity. So that is what conductive and photo, because you are applying the light energy. That is what photoconductive effect is going to. Okay. Okay, we'll take break for 15 minutes. Okay, so it is 11:20. We'll meet at 11:35. Okay, thank you. Yeah, welcome back, students. Yeah, let me go to this properties of semiconductor. I'll clarify some of the doubts and all. Okay. Anyhow, some of you are asking about the coverage of the syllabus and all. I'll discuss. Okay. Still, we have not entered into the subject. Okay. What I have done up to now is we must understand what is the importance of the semiconductor material or why I am choosing this. Okay, and I've given the very broad perspective that what we are going to discuss. Okay, so if you consider this systems in electrical engineering, okay, starting with this, then we have considered the three different things here. One is the important thing is the terminal characteristics which we must obtain. Okay, now these terminal characteristics are going to dependent on what type of material and material parameters that are going to be, and the ambient conditions, obviously. Is it fine? Okay, now uh, if you consider here, when you go for AC transient, you know what is meant by transient. Okay, so in the transient conditions, still your parameters are dependent on the time. That's why I'm writing it as I of t and V of t. But when you go for steady state analysis or small signal, already it has been reached the steady state. So it will not depend on time now. That's why simply I'm writing as IV. Okay, hope I am clear. Okay. Now coming to the different properties. Okay. So this starting with the first one, polarity of charge carriers. Okay, so what is this polarity of charge carriers? You have two types of charge carriers here. One is the electron, the other one is the hole. Okay, this we are going to discuss in detail, please. Okay, why I'm having electron and hole in the semiconductor, we'll discuss in detail, and we'll discuss about what is this hole actually. Okay, hole actually in detail. Okay, don't worry. Okay, don't worry about it. Okay, we'll discuss in detail. Then coming to the second property, what is concentration of charge carriers? Because see, what is the conductivity of the material? Sigma is equal to n into q into mu n. Yes or no? Yes, sigma is n into q into mu n. If it is only electrons are present. Now, if holes are also present, then one more term you have to add, which is P into Q into mu P. Am I correct? Okay. Now, this sigma depends on what parameters anyhow. Q is the charge, okay, which is 1.6 into 10 power minus 19 coulombs. Anyhow, for our discussion, mu and mu P are the mobilities of electron and holes. They are going to be constant. Okay. And on what parameters now the sigma is going to depend? Obviously, the number of electrons and holes. Yes or no? Okay. And that is what we have explained here actually. So I'm taking the carrier concentration on the x-axis. If the carrier concentration is less than or equal to this 10 power 6 per centimeter cube, that type of material we are calling it as what? Insulator. And if it is more than or equal to this 10 power 21 per centimeter cube, we'll call it as what? Conductor or metal. And in between, that is 10 power 16 per centimeter cube to 10 power 21. Okay, so here you can say specifically electron concentration here. Okay, then this is called as what? Semiconductor material. This is the very important point that you must understand. You can vary the carrier concentration of 15 orders of magnitude. You can see 10 power 6 to 10 power 21. Okay, so this is the very interesting property of the semiconductor material. Okay, so doping and illumination, and by changing the temperature you can do this. Okay, again this boundary, whatever we have written here, this value, they may not be the sharp edges. Okay, hope I am clear. Then coming to the third property, that is how you are making these charges to move from one place to the other place, which results in the current. Yes sir. Okay, you have to make them to move, and you can have drift current, So how you are getting this drift current? By creating the potential gradient, nothing but there is an electric field that is going to be developed. This electric field will make the charges to drift from one place to the other place. And that type of current, we are calling it as what? Drift current. Am I clear? Now coming to the next type of current, possible current is what? Diffusion current. How? Due to the concentration gradient. Okay, by creating the concentration gradient, you can get this diffusion current. And another one is thermoelectric current. Why? Due to temperature gradient. If you create the temperature gradient, okay, then you can have this type of current, which is called as thermoelectric current. Yeah, here if you consider the conductor, there is no possibility of getting diffusion. Try to understand the basic mechanism of the diffusion, then you can get whether it is possible or not. Okay, there are some of you have asked why it is not significant in the metal. Okay, the diffusion and thermoelectric currents. Okay, because it's the nature of your metal or semiconductor material. Okay, so try to understand why I'm getting or how the current is produced because of these processes. Then you can get answer on your own. Okay, so these two, diffusion current and thermoelectric current, they are going to be significant in case of semiconductor material, but not in metal. Okay, almost we can you can say it's not possible also. Okay, now when you go for the fourth property, interaction with electromagnetic field, yeah, please try to concentrate, there are many doubts on this. Okay, now when you illuminate the semiconductor material, what will happen? The light energy will be absorbed by the material. Okay, then there is a generation of electron hole pair. Please try to understand. Anyhow, this again we'll discuss in detail later. Generation of electron hole pair means you are placing the electron from valence band to conduction band. Now from which place or which bond the electron has been moved from valence band to conduction band, there is a vacancy of electron. That vacancy, okay, or incomplete bond, we are going to refer it as hole. Please try to understand. Okay, incomplete bond or vacancy, we are going to refer it as what? Hole. So that is why I'm getting electron hole pair. And this is EHP is what? Electron hole pair. Okay, now why I'm calling it as photoconductive effect here? The name itself. So try to understand the name, you can get many things. Okay, conductivity, from that you are getting conductive. Okay, photo, what is the input here? You are applying the light energy, so it is photoconductive effect. Okay, so you have given some example devices here, LDR, light dependent resistor, photodiode. Okay, anyhow, how it is going to work and all we'll discuss later in detail. Okay, don't worry about it. Okay, how photodiode is going to work, we'll discuss in detail with the numericals also. Don't worry, please. Okay, now with a little modification, we can get another effect called as the photovoltaic effect. Okay, so what is photovoltaic effect is, if you can able to observe an open circuit voltage, okay, or voltage across an illuminated semiconductor material, open circuited semiconductor, PN junction, then I can call it as photovoltaic effect. Again, please, we'll discuss this also in detail, solar cell in the optoelectronic devices. Please don't worry. Okay, I'll get clarify all the doubts that you are asking. Okay, be patient. Okay, this is only the starting class. No, I'm just giving the glimpse of whatever we are going to discuss. Okay, as a broad perspective. Don't worry. By the end of the subject is completed, I can say 90 to 95. Okay, more than 95% of your doubts will be get clarified. Please don't worry. Okay, but what I am expecting from you is you need to be regular to the class. You have to listen with concentration, please. This is what you have to do from your side. Okay, so from my side I'll do my best. Okay, don't worry. Okay, now what is the second possibility? When you generate the electron hole pair, okay, you are exciting the electron actually. So it is not your equilibrium state of the electron. What will happen? It will come back to its valence band. May not be into the same vacancy where it has been move into the conduction band, but it will definitely come back to valence band. Okay. While coming back, we can very clearly see conduction band energy level is at higher energy level than the valence band. Then this difference amount will be given as energy. There is two possibilities. It can be dissipated as heat. It can be given as some light energy. Okay. So the light energy can be observed. This possibility is only in the direct band gap semiconductor materials. Again, this we'll see. Okay. Direct band gap semiconductors. Okay. So whatever the light energy that we are observing here, this is possible in where? Direct band gap semiconductor. Okay. There are other type of material called as indirect band gap semiconductor. So that there it is going to be dissipated as heat. It will not produce any light energy. Hope I am clear. Now, whenever the output is a light energy, okay, it is called as what? Luminescence. That process is called as what? Luminescence. Then why I am getting? Because of this electron hole pairs that are generated. So it is electroluminescence. So here input is electrical energy, output is going to be the light energy. In the examples again, we can have LED laser. Again, please don't worry. We'll again discuss this LED laser in detail later, how it is going to work and all. Okay. Then now the third possibility is this one. Okay, like this. So it is absorbing the light energy, getting the electron hole pair, and then again recombining like this. I'm getting. So definitely nu2 will be less than nu1. I think you know what this energy of the photon E is equal to what? H nu. I think you know what is this H and nu is. H is nothing but what? Planck's constant. It is Planck's constant. Okay, what is nu here? Frequency. Hope you know this. Okay, this is the energy of the photon. H nu is nothing but what? Energy of the photon that is going to incident, light energy. Okay. So this process again, light is the output is the light energy. So I can call it as luminescence, but here input is what? Light energy. So it is called as what? Photoluminescence. Okay. I think this till this we have discussed. Okay. Yeah, please again I'm mentioning, don't worry. Okay, I'll make you to get all the concepts. Okay, we'll go step by step. So till I have not given any syllabus here, I will discuss that, because what I have discussed till now is what is the importance. Okay, we must know the importance of that subject, and that is the reason why I have given all these things. Okay, hope I am clear. Now let us consider the syllabus that what we are going to consider. Okay, we'll see briefly what we are going to discuss topic by topic. Okay, so we are going to start with considering the syllabus. Okay, we'll start with very important one, semiconductor theory. First topic is what? Semiconductor theory. It is semiconductor theory. Yeah, this is very important one. Why? Because your electronic devices are going to be made up of what? Semiconductor material. So you must understand the different properties or various properties or characteristics of the semiconductor material. Then your things will get easy further. Okay. So this part, okay, is going to be very important one. Okay, please try to concentrate on this semiconductor theory. Then we'll go for the devices. Once the theory, semiconductor theory is over, we'll go for the first type of semiconductor device, which is PN junction. What it is? PN junction. Okay. Then we'll try to discuss about special purpose diodes. Okay, special purpose. Okay, special purpose diodes. So here in this we are going to discuss about the Varactor diode, Zener diode, tunnel diode. These are the three things that we are going to discuss in the special purpose device, special purpose diodes: varactor diode, Zener diode, and tunnel diode. Okay, so please try to, again, when we are going for each, topic, I'll give very clearly what we are going to discuss. Okay, then we'll discuss about optoelectronic devices. What it is? Optoelectronic devices. So the name itself is giving, okay, optoelectronic devices. They're like, we're starting with the, photoconductor, photodiode. Again, photodiode, you have pin diode and avalanche photodiode we are going to discuss. Then solar cell. And another category is light emitting diode and lasers. These we are going to discuss in optoelectronic devices. Okay, yes. Now, once this part is over, okay, so then we need to discuss about transistor. What it is? Transistor. So usually this transistor, you can have two categories. One is called as bipolar and another one is called as unipolar. So the name itself is giving, okay, if you read the name carefully, you can get it. Bi means what? Two. Polar is the polarity. Okay, so the current which we are going to get is going to be because of both the types of carriers, that is electron as well as the hole. Okay, now you can give example for this is nothing but BJT. What is BJT? Bipolar junction transistor. Okay, and here you can have two types of things. One is called NPN transistor and another one is PNP transistor. Is it fine? Okay, now coming to the unipolar, again you can very clearly see with the name itself is indicating uni means one, polar is the polarity. So current is either due to electrons or holes, any one type of carrier. Okay, so it is the example, you can give it as field effect transistor. What it is? Field effect transistor. So in this one we are going to discuss about JFET, that is junction field effect transistor, and another one is called MOSFET. What is this? Metal oxide semiconductor field effect transistor. Hope I am clear. Okay, so junction field effect transistor, this is MOSFET is metal oxide semiconductor field effect transistor. Is it fine? Okay, so see the order, we'll discuss a bipolar, that is BJT, and then we'll go for JFET. Okay, so again I'll write here the order that we are going to follow. We'll start with BJT, we'll discuss first, then we'll go for JFET, and before going to the MOSFET, we'll discuss one important concept called as MOS capacitor. Okay, because if you understand the MOS capacitor, your 80% of the MOSFET is completed. Okay, only the thing, the characteristics that you need to get, we'll see how. Okay, yes. Okay, so this is the MOS capacitor. After BJT we'll go for JFET, MOS capacitor, and after this we'll discuss about MOSFET. Okay, and then CMOS. What is the CMOS? Complementary metal oxide semiconductor. So in this particularly we are going to discuss about CMOS inverter. Particularly we'll discuss about what? CMOS inverter. That is what we are going to. Okay, yeah, maybe in your material and or this was given as EDC and VLSI. That's your convenient way of classifying it, but this is as a whole. Okay, I think our schedule is up to BJT, I think. Okay, and later on we'll go for JFET, MOS capacitor, and other also. Okay, so these are the different topics that we need to understand, okay, very thoroughly. See, again I am mentioning this point, please pay attention. If you can able to understand thoroughly these two topics, the semiconductor theory and the PN junction. Okay, I can say 80% of the concepts are going to be completed. 80%, because what we are going to consider later on in the other devices, it's going to be implemented or taken from the semiconductor theory or the PN junction. Please keep it in mind. Okay, if you get thorough with the semiconductor theory and PN junction, the other characteristics, diode device characteristics, you can very easily understand. Okay, so for that reason we are going to spend good amount of time to understand the semiconductor theory and the PN junction. So again, my request from my side is, please take it for granted that whatever I am teaching is required for you. Don't have second thought whether these things are necessary or not. Yes, it is necessary for you. Okay, so hope I am clear. Okay, so these are the things that we need to consider one by one. Again, I'm repeating, semiconductor theory, PN junction, if you can able to understand thoroughly, the other device characteristics, other device topics are going to be very easy for you. Only the thing, we are repeating the thing. Okay, repeating the things. So, and one more important point, what you must understand here is, don't read the topics separately. There will be a link, there will be some connection from one topic to the other topic, continuation. If you can able to get that, okay, it's going to be very easy for you. Okay, and I'll try to make that link. Okay, I'll give that link to you. Okay, so that there will be a continuous flow of, okay, so that you can feel very comfortable. So from my side, okay, there is no doubt that I'll give the whatever you require, but from your side, what I'm expecting is your dedication, your commitment. Okay, now coming to the weightage, some of you are asking the weightage. Okay, on an average you can expect around 9 or 8 to 12 marks, 8 to 12 marks. Okay, in case of ESC. Okay, in case of gate, sorry, and more than that in case of ESC. Okay, and another important point what you must understand here is, this subject is the basic for particularly electronic devices. Okay, electronic ECE students. Okay, because if you want to understand the analog circuits or analog electronics where the application part is going to be present, okay, you must understand the device characteristics thoroughly. Yes or no? See, your device is made up of semiconductor material. So to understand the device, you must have the thorough understanding of the semiconductor material, and that is what we are dealing with, semiconductor. Then once you get understanding, you must have the understanding of the devices. That is what we are going to discuss, entire electronic devices. Then comes the application part. So if you thorough with this electronic devices, your application part is going to be easy for you. Okay, hope I am clear with whatever I have given. Okay, yes. Now, so the first topic that what we need to consider is what? Semiconductor theory. Again, so if you consider this semiconductor theory, okay, so this will try to make it into 4 parts. Okay, yeah, again, from my side, a small request is, you might have adapted some type of learning the things. Okay, you have already practicing. Okay, there will be little change from that. Okay, my intention is, initially you are going to be dependent on me, definitely. Okay, so you just follow blindly, and as the course progresses, I must make you to independent of me. Okay, because I cannot available every time. Okay, but I'll give the necessary concepts, definitely. There is no doubt about it. Okay. Okay. Hope I am clear. Now, in the semiconductor theory, we are going to start with equilibrium carrier concentration. What it is? Equilibrium carrier concentration. Okay. Again, the classification is a logical thing which you can easily understand. Okay, then we'll go for, so you can very clearly see what is equilibrium. Again, these terms will define it later. Okay, you have many times used the word called as equilibrium and steady state, but without understanding. We'll try to get clarified with the both the terms. Okay. Now, why I am considering equilibrium carrier concentration? Because if you see what is the conductivity formula that we have given, sigma depends on what? Carrier concentrations. Sigma depends on carrier concentrations. So I must know under equilibrium condition how many number of charge carriers are present. That is what we are going to discuss in this topic, first topic. Okay. And the second one is, I know that I have the charge carriers. Now you must move these charge carriers from one place to the other place. No. So what it is called? Transport of charge carriers. What it is? Transport of carriers. Transport of what? Carriers. Okay. Anyhow, we have given three types of things here, but we don't consider here thermoelectric currents. We'll discuss only about drift and diffusion. That is enough for us. Okay. We don't consider thermoelectric currents. We'll discuss about drift and diffusion currents here in this case. Okay. And the third one is, again, this is the interesting property or topic of semiconductor theory, which is called as excess carriers. What it is? Excess carriers. Because I need to modify the electrical properties. No, if you see the second property that we have given, concentration of charge carriers or carriers. Okay, you can vary the carrier concentration from 10 power 6 per centimeter cube to 10 power 25 per centimeter cube. And we have given there are different ways of modifying this. So that we are going to discuss here, excess carriers, and how they are going to vary with respect to time, with respect to distance and all, we are going to discuss in the excess carriers. Okay. And finally, this is also a very important one. We are going to give common procedure to analyze the device. What it is? Common procedure to analyze any device. So we'll go for procedure. Okay. We'll discuss about procedure for device analysis. Device analysis. Okay, hope I am clear. So these are the things that we are going to discuss with respect to what? Semiconductor theory. Starting with equilibrium carrier concentration, then we'll go for transport of carriers, then we'll discuss about excess carriers, and finally procedure for device analysis. Okay. See, again, I'm mentioning this point. You need to be thorough with this semiconductor theory to understand the other any type of device you are going to consider in the EDC. Okay, and that is the reason why we are going to spend a lot of time. We'll go by step. Okay, try to understand, concentrate, and understand these things. Then other devices are going to be very easy for you. So again, this point I'm repeating that semiconductor theory and the PN junction, if you can able to understand, this is going to be repetition in the other devices. Okay, so hope I'm clear with whatever I've given. Okay, yeah. So any valid doubts that you have, you can ask me. I'll try to clarify them. And yeah, I'll give my mail ID. You can mail the doubts. Okay, and also you can, if you I think Telegram channel is that. For that also you can send your queries. Okay, so let me write my mail ID. It is ED and electromagnetics at gmail.com. Okay, yeah, you can send your queries to this. Okay. Okay, so as and when I have time, I'll respond. Okay, don't worry. Okay, I'll respond. Okay, so it is EDN electromagnetics gmail.com. Okay, so you can send these queries. I'll write my name also. Okay, otherwise you can send to the Telegram channel that we have. Okay, so that also you can use Telegram channel. Okay, yeah, now we'll go for doubt clarification.
Hello.
Yeah. Yes.
Hello, sir. Good afternoon, sir.
Yeah, good afternoon. Very good afternoon.
Sir, actually, mine is just a small request. Actually,
Yeah.
Actually, 2.5 years I had taking this gate coaching. So, if any basics are there, please let me know because that will be
No. Come again. I am not getting. You are taking gate coaching?
like after 2 years. Actually, I started taking gate coaching. Actually,
Fine.
so if any basics are there, if anything missed, please cover them, sir. Because if you want,
See, that's what I'm telling you. Know, if you listen to my lecture starting from that,
right.
I'm initially I'm assuming that you don't know anything.
Yeah.
Okay.
Okay,
From
sir.
the basics, very basic things I'm going to teach. Okay. Very
Okay.
basic things.
Okay, sir.
Okay. And then we'll go for once the basics are we get thorough with the basics, then you can answer any type of question on any topic. You can deal it. That is my approach. Okay. Don't worry. Okay.
Okay, sir. Thank you, sir. That will be
Yeah.
helpful.
Yeah. Thank you. Thank you. Hello.
బావా సేల్ లేదు బావా చూడు బావా కొంచెం
Hello.
ఎక్కడ పెడతా హైదరాబాద్ లో ఎవ్వరు లేడు ఇప్పుడు మా ఓన్ వాడు కూడా దాని కూడా లేదు
Hello.
సార్ హలో
Yeah.
హలో
Yes. Go ahead.
హలో
Hello. Can you able to hear me?
హలో
Yes. Can you able to hear me?
సార్ జస్ట్ నో క్లారిఫైడ్ సార్
Yes.
హలో
Yeah. You got clarified. Fine.
లేదు హలో
Yeah. Hello.
ఇట్స్ క్లారిఫైడ్ సార్
Okay. వీళ్ళు అడగలేదు ఇంకా
స్టూడెంట్ చెప్పండి అన్మ్యూట్ చేసుకోండి
Yeah, Jyoti Priya, please unmute your voice and you can raise the question. Jyoti Priya, yes. You can unmute your voice and you can raise the question.
Hello, sir.
Yeah.
Sir, no doubts, sir.
Okay. So you have raised the hand. That's why I called you. No problem.
Okay, sir.
Fine. ఇవి మారిపోతున్నాయి సార్. యా మయూరేష్.
Yes, sir.
యా
Actually, you give two definitions.
యా I'm not able to hear your voice. Please, I think you need to increase your volume. Hello.
Hello.
Yeah.
Are you able to hear me, sir?
No. It's very very low voice I'm getting.
Now, sir.
Yeah, fine. Go ahead.
Sir, you gave two definition that a device which can perform amplification
Yeah.
and the device which perform as switching that can be used as active devices.
Yeah.
I don't get that, sir.
How means?
Means how we can say that if the needs
It
device
is the definition. See, definition means you must what you can call, if any device can able to amplify, it's a basic definition. Okay.
But sir, it is not storing charge or it is not giving any means energy, right?
Yeah, that's what. See, if you see the first definition that what we have given, let me go through that. First definition is what? That is what you are asking, no? First definition is what? A device which can
Act as a source.
add a source. Yeah,
Yes.
that is one category.
Yeah.
Okay.
Okay.
The other, not only that, a device which can able to perform these two operations also, you can call it as active device.
Okay.
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 Because till now we know only the first definition we have as an active.
Yes.
Yes or no?
Yes, sir.
Am I clear?
Yes, sir.
Yeah. Any other doubts?
No, sir.
Thank you.
Thank you.
Yeah.
Hello, sir.
Venkati.
Good afternoon, sir.
Yeah. Good afternoon.
Sir, what is MEMS, sir?
Yeah, it is micro electromechanical system. I think I have written, no? Let me check.
Yes.
Yeah. You can see micro electromechanical system. It is one type of system.
Okay.
Similarly, next one is the nano electromechanical system.
Okay. Yes. Sir, what is the drift current, sir?
Yeah, still we are not getting to that. No, we'll discuss in the transport of carriers. We'll discuss in detail what is drift and diffusion. Don't worry. Okay.
Okay. Sir, what will be the everyday schedule, sir? How it will be done?
Yeah, I think that will be communicated by others. I think it is 9 to 1 every day.
Sir, means 9 to 1 means from 9 to 1 total class will be there, sir, or
Yeah, doubt clarification
it
session
will
will be also there.
at 12 o'clock, sir, or in
No, I think
between?
it will be 15 minutes. We'll take the break in between and 15 minutes for the doubt clarification. Again, at the end of the session, again, we'll have 15 to 20 minutes doubt clarification session.
Okay, sir. Thank you, sir.
Yeah. My duration is over.
Hello.
Yeah. Shubham.
Hello.
go ahead.
Can you hear me, sir?
Yeah. Go ahead.
Sir, you said that after electrons move from valence band to valence band to conduction band,
Yeah.
then we have studied about the stimulated emission. In that case,
Yes. See. 1 second. Still, we have not entered into that stimulated emission and all. No. We'll discuss very clearly in the laser and LED. Okay. Okay. Go ahead. What is your doubt? Go ahead. Shubham, go ahead.
when the electron moves from valence band to conduction band, after
Fine.
that, it will fall again to valence band, or what will happen?
Yeah, that's what. When it is coming back to valence band, there is a difference now from one energy level, higher energy level to lower energy level, the electron is coming. Fine. Now there is a difference of energy. What that energy is going to be? What will happen to that energy? Either it can be dissipated as heat. In some way it has to come out.
Yeah.
So it can be dissipated as heat is the one possibility.
Right.
If that frequency or the wavelength is matching to the particular color, that is going to be visible for us. So whatever the light energy that I'm getting, that luminescence process that I have given there, it cannot happen in every type of material. It can happen only in direct band gap semiconductor. We'll see what is the direct band gap and what is indirect band gap later.
Okay, so can I
Clear?
so
Yes?
can I say that when
Shubham, I am not able to hear you.
hello sir, hello.
Hello?
Can I say that when
Yeah, I am
whenever
not getting your voice. Earlier I got very clearly, but I am not getting now.
so can I hello
No,
hello
I am not getting. Very low voice I am getting. Please.
uh, hello
Shubham, I am
hello.
not getting your voice. It is very low, very low.
Hello, sir.
Yeah, tell me.
Sir, can I say that when light is absorbing means when light is an input, that time valence band to electron will move from valence band to conduction band, and
Yes, that is.
that is the basic. Okay.
Yeah. Not only light, somehow you are giving energy to the electron. One way giving is the light energy.
Okay. Okay.
So if you give energy, then electron can move from valence band to conduction band. How you are giving, there will be different ways.
Okay.
Is it
Thank you.
fine?
Okay. Yes, sir.
Yeah, thank you.
Hello, sir.
Yeah,
Good morning, sir.
good morning. Good morning.
Sir, my doubt is about the thermoelectric current, sir.
Okay, fine.
Sir, this is due to the temperature giving in the semiconductor. With various parts, the temperature will be different, no, sir.
Uh-huh.
And then the concentration will change, no, sir, for the carrier.
No. See, anyhow, this thermoelectric current also we don't consider in our discussion of semiconductor. Okay, I've given there is other possibilities also. But anyhow, you are asking doubt. I will clarify it. When you create the temperature difference, there are two ways. One is the concentration can change. Other one is okay. Anyhow, this again mathematically we will discuss later. Okay, the velocity with which the charge carriers are going to move also changes. No.
Yes, sir.
Yes, sir. Because energy is going to be different, definitely.
Yes, sir.
One way you can generate the concentration, I mean, extra carriers. The other
sir.
way is the same energy can be given to the charges so that they can move with a higher energy, a higher velocity.
Yes, sir.
So in that case also current can be possible.
Yes, sir.
But anyhow, we don't consider, okay, for for our course, it is not required.
Sir,
But there is a possibility.
sir, the temperature gradient will have the effect of both on drift and diffusion current. Can I say like that, sir?
No, because yeah, that's what I'm telling you. These three currents, when you are discussing about the carrier transport, no,
Yes, sir.
with mathematical equations, I will explain. There you will get clarified. Okay, don't worry. Huh?
Okay, sir. Okay, sir. Thank you.
Okay, am I clear?
Yes, sir. Yes, sir.
With mathematical equations, we'll try to explain that. There you will get clarify what this is.
Yes. Sir, actually, I thought the drift current is based on the VD, no, sir, velocity, and the diffusion is
Drift current is based on
VD, sir, velocity.
drift velocity, and that is how you are getting velocity by applying electric field only. No, electric field is nothing but what? Concentration. Sorry, potential gradient only. No.
Yes, sir. Because of temperature, you said that it will change, no, sir.
Huh.
And so I thought that the temperature gradient will have effect on drift due to velocity.
That's what I'm telling you. See, for all these three mechanisms, that is drift, diffusion, thermoelectric current, there is a common basis.
Okay. Okay.
Okay, that common basis, with that common basis, we'll discuss these three things in detail with the mathematical equations later.
Okay, sir. Thanks.
Fine?
Yes, sir.
Yeah, thank you. Yeah, I don't have this name. 16011777350. Please unmute and ask the question. Please unmute your voice and you can raise the doubt. Yeah, Pranay. Pranay, you can unmute and ask the question.
In the properties of semiconductors, sir,
Yeah,
the fourth one, interaction with electromagnetic field.
fine.
You have discussed mostly about the light energy, no, sir, rather than electromagnetic field. It is only small part, no, sir.
Yeah, what is electromagnetic field?
The electric field and magnetic field propagation by complementing each other, sir. EM wave.
See, suppose you consider an atom.
Yes, sir.
You consider an atom. Okay. In atom, what you are going to have? At the center, you are going to have the protons and neutrons.
Yes, sir.
Protons are positively charged. Surrounding that, you are going to have the electrons. Electrons are negatively charged. Now, these electrons are revolving around the nucleus. Yes or no?
Yes, sir.
So, how you are getting electromagnetic? Electric field, suppose if I have a source, what is the source? Basic source of electric field is the charge. Am I correct?
Yes, sir.
If charge is under rest or stationary condition, then I will get electrostatic field. Please try to concentrate, okay?
Yes, sir.
Now, if the charge is moving with uniform velocity, charge is moving with uniform velocity, what field you are going to get? Anyhow, whenever there is a charge, electric field there is going
Magnetic.
to. Now, apart from electric field, now there is a magnetic field also.
Yes,
Because
sir.
charges are moving with uniform velocity means what? Current is going to flow through the material. Now, what will happen? There is a magnetic field. What is that magnetic field? It is going to be static. Hope I am clear.
Yes, sir.
Is it fine?
Okay, sir.
Now the same charge is moving with non-uniform velocity, then I am going to get electromagnetic field. Okay. Now there are two levels, micro level and macro level. Okay.
Yes,
So in our discussions, what we are going to take is electric field and magnetic field are going to be independent. Can you make it independent now? Even take an atom, can you make electric and magnetic field independent?
No, sir.
Yeah. So that is also present, no?
Yes, sir.
So that is one way you can understand. Okay. But anyhow, that properties what I have listed, I have just given the what do you call? I have not given any details as no. The circuit I have not given, the device I have not given, I have not explained anything there. Just I have given a glimpse only. Are you getting
Okay,
my
sir.
point?
Yes, sir. What I thought is electromagnetic.
What is photodiode? Yeah, I'll clarify. Photodiode is what? You are going to operate the PN junction in the reverse bias. Across the depletion region, you are going to illuminate.
Yes, sir.
Okay. So now you are applying the reverse bias. You are going to have the electric field as well as the magnetic field also, no?
Okay, sir.
Is my point clear?
Yes, sir.
So here I am not given that much detail. Just I have because it's not required here. Just summary I have given here. Is it fine?
Yes, sir. Thank you, sir.
Yeah. Good. Yeah. Rahul.
Hello.
Yeah.
Sir, could you keep the tests on a weekly basis rather than when the whole subject is completed? Could you take that to
I'm not getting your question.
Like tests అనేవి like every week పెడతారా like?
Yeah, that I think that will be given by some other. No,
Yeah.
I think
Like
you can contact Venkat Reddy sir. Venkat
Okay.
Reddy sir, you can.
Fine.
Yeah, any technical, subject doubt, you can ask me. I can clarify. Yes. Rahul.
Okay, sir. Fine. I got it.
Okay. Thank you. Yeah. Harsha. Hello.
Good morning, sir.
Good morning.
Sir, am I audible?
Yes. Go ahead.
Sir, you told that in diffusion current it is due to the concentration gradient, no, sir?
Yes.
That concentration is due to the minority or majority or both?
No, concentration gradient is not with respect to your minority, majority. No. Minority and majority carriers are what type of material you are considering and what type of charge carriers you are considering. If you take P-type, in P-type semiconductor, what are majority carriers? Holes.
Holes.
then electrons are the minority
Yes,
chemistry.
sir.
With respect to that, you need to talk.
Yes.
Are you getting my point?
Yes, sir.
So there is no meaning whether it is concentration gradient is okay. It can be for both also, majority as well as
Like
minority.
in a whole, we should take or consider it.
Uh-huh.
In a whole, we should consider it, sir.
Yeah, I'm not getting your voice. There is no clarity in your voice.
Hello.
Yeah, it is
In a
okay.
in a whole, we should consider it, sir. Then.
Yeah, that's what
Like,
I'm telling you. We'll discuss in the when you are going for particular transport of. I have given the semiconductor theory. There are 4 topics, no?
Yes, sir.
So,
Sir, and
yeah.
I'm a little bit confused in that electron hole pair recombination and generation. I got like the electron when moving from valence band to conduction band, then it will generate a electron hole pair, no, sir?
Yes, definitely.
That will be recombination.
No, generation means it is electron is moving from valence band to conduction band.
Yes, sir.
Recombination means an electron from conduction band should move into valence band.
Okay, that will happen when the electron loses its energy, right, sir?
Obviously, because it is excited state, no? When you make electron from valence band to conduction band is the excited state. It cannot stay forever.
Yes, sir.
It should come back. Okay.
Yes, sir.
So when it is coming back, that process we'll call it as recombination process.
Okay, sir. Thank you, sir.
Yeah.
Good morning, sir.
Good morning, Lakshmikant.
Sir, you told that electron hole pair will be created when we supply some energy. When they are going to recombine, sir, again?
See, that's what. See, if you remember your basic physics or chemistry, you will have ground level, no?
Yes, sir.
Then level 1, level 2, like that it is going to be.
Yes, sir.
Now, if you want to make your electron to present in the, suppose ground level is E0, then E1, E2 like that.
Yes, sir.
If you want to make your electron to move from E0 to E1, obviously you require some energy. Yes or no?
Yes, sir.
But now, once the electron is entered into the E1, it is at higher energy.
Yes, sir.
Is there any effort to put to make your electron to come from E1 to E0?
When it loses energy, it comes back, sir, again.
Obviously, that's what it is happening, because valence band, conduction band, if you take, conduction band is at higher energy than your valence band, no?
Yes, sir.
So automatically it will come back to valence band. In that process, we'll get difference energy.
Sir, Zener diode is a passive device. Is it correct, sir?
Zener diode?
Passive device.
Because we are very clearly given what should be the characteristics of an active device.
Yes, sir.
Yes.
Yes, sir.
Fine. Yeah. Any other doubts?
No doubt. Thank you.
Okay. Yeah, this 16011773548. Please unmute your voice, and if you have any doubt, you can raise. Yeah, Gopal Krishna, please unmute your voice and you can ask the doubt.
So, good afternoon, sir. Am I audible?
Yeah.
Sir, I wanted to ask that you classified systems in electrical engineering into two. One is energy systems and information systems. Can you please give some examples, sir, or at least elaborate some?
No, I'm not getting your voice. You want what?
You classified systems in electrical engineering as energy systems and information systems.
Fine.
Can you please give examples of either of them? Sir?
Example means what? I'm not getting.
Which systems can be classified into energy systems and which were into information systems? Like for example, there is some diode or something. It is under.
It's not like that. See, any system you consider, what you are going to do with that. Suppose, okay, you take distribution of the electrical energy. You have transformers, electricity is there, no?
Yes, sir.
So there is one energy. One system has to deal with that energy, no? So where you are getting that energy, somewhere it has to be generated.
Yes, sir.
Once you are generating it, then you have to distribute.
Yes, sir.
When you are distributing, it is not like whatever you want you can distribute. You have to regulate also for depending upon the specifications for different subsystems. You have to give a certain energy, not like whatever you want.
Voltage. Yes, sir. Yes, sir.
And along with that, you should have the information. For example, to which subsystem you are giving, and what are the specifications, and all other information you should have. No.
Yes, sir.
There comes this information. This is this classification.
Yes.
One second. This classification is our convenience. Okay.
Yes.
Are you getting my point?
Yes, sir. I'm getting. So I would like to ask that in the example you just told in power distribution system, where does this semiconductor come into place?
Yeah, there are many components that are going to be present. No.
Yes, sir.
See, suppose you consider only a switch.
Yes, sir.
The switch you consider.
Yes.
We are going to use SCR, silicon control rectifier. So what type of, there will be 4 layers, PN.
PN, yes, sir.
Yeah, that is a semiconductor material only, no? So just I have given one simple example.
Yes.
So like that, there are many other things that you have to implement.
Okay.
Is it
Thank
fine?
you. Yes, sir. Yes. Thank you very much.
Okay. Yeah, Harris, please unmute and you can ask the question.
Good afternoon, sir.
Good afternoon.
Yeah, so I would like to ask whether you will be covering our VLSI part also.
Yeah, that's what I'm telling you. This classification EDC VLSI is our convenient way. I think that is also. I think for right now they have given up to BJT, bipolar junction transistor. I think.
All right.
Anyhow, we'll cover the other VLSI part also, definitely.
Okay.
Yeah. Any other technical question?
No. Thank you so much.
Yeah. Yeah. Priyadarshini, please unmute and ask the question.
Vena. Good afternoon, sir.
Good afternoon.
Sir, all the 3 terminal devices are active or not, sir?
No. That is one characteristics. No. Yeah. You are not supposed to take it for granted. Okay. The 3 definitions we have given. No. 3 if it is fitting to any one of these 3, then you can call it as active. And in that process, you may have 3 terminal device into what? Active device. You cannot conclude it.
Okay, sir.
Okay. But it should fit into any one of these 3 definitions. Then you can call it. Is it fine?
Okay, sir.
Okay.
Okay, sir. Thank you.
Yeah.
Hello, sir.
Yes.
Actually, sir, what if energy gap is 0 and overlap is not there? Then whether the device is insulator, conductor, or semiconductor?
No, I'm not getting your question. Please come again.
Sir, if the energy gap between 2 bands is 0, means they are neither overlapping, neither we have some energy gap between them. So
No, obviously, no. See, if you see the band diagram, which I have drawn for metal or conductor, so there is an overlap. No, you cannot in this region where I have put the green lines. You cannot say which is conduction band and which is valence band. Now, the electrons which are going to be present in the conduction band, they are responsible for the current.
Okay.
They are called as the free electrons, and they are responsible for current, not the electrons which are present in the valence band. Valence band, still they are bound. Okay. There will be a covalent bonds. If you take the silicon, fourth group element, adjacent 4 silicon atoms will be there. They are bonding, they are forming the bond. They are not the free electrons. So they cannot produce any current. But the electrons which are present in the conduction band, they are free electrons, and they will give. Hope I am clear.
Yes, sir. Means every device must fall in these three categories only. There
Obviously.
are no other. Okay, okay, sir.
There will be superconductors also, but for our discussion, this is enough.
Okay, sir. That's all. Thank you.
Yeah. Yes, Shrikant, please unmute your voice and you can raise the question.
Sir, you have actually unmuted me. I have asked my doubt.
Oh, okay. Sorry. You can go ahead now.
No, sir. I have asked my doubt and you clarified that energy band.
Oh, okay, okay. Fine, fine, fine.
Okay.
Yeah.
Hello, sir.
Yes.
So I have some technical issues, so that's why the hand raising.
Yeah, fine. Technical issue, huh?
Okay. Yes,
Now
sir.
it is resolved. Hello.
Hello.
Yeah, is it okay now for you? Sonu? Hello, Sonu?
Yes, sir. Now it's okay for me, sir.
Okay, fine, fine.
Hello.
Hello.
Good afternoon, sir.
Good afternoon.
Sir, actually for us, analog electronics has already started.
Fine.
But you have said that this would be basics for that.
Basics for?
Analog electronics, no, sir. So, how already we studied these basics in analog electronics, sir. Transistors basics, semiconductors basics.
Okay.
How this would be helpful, sir, again?
That's what I'm telling you, no. See, in when the analog faculty is dealing, they will give very brief, whatever, very few things that they are going to discuss. If you want in-depth analysis, then you must, because what you are discussing here is the device characteristics, basically.
Yes, sir.
And what you are using for application part.
Yes, okay.
Analog means application part. So if you have get thorough with the characteristics, it will be better.
Okay. Okay, sir. Thank you,
Right?
sir.
Yeah.
Hello.
Hello.
Hello, sir. Good afternoon, sir.
Good afternoon.
Sir, what's the difference between where do we use this MEMS and NEMS, sir? Micro electromechanical.
See, they are one type of systems. Okay. There are many applications for micro electromechanical systems and nano electromechanical. Some brief, types of devices that are possible. Okay.
Okay, sir.
Anyhow, that we are not going to discuss in our EDC subject. I've just given a few examples.
Okay. Okay, sir. Thank you, sir.
Okay, fine.
Hello, sir. Hello.
Hello.
Hello, sir.
Yeah.
Sir, actually, what is the definition of transducer?
I'm not getting your voice. What is?
Hello, sir.
Yeah. Go ahead.
Hello.
Yes.
Sir, what is the transducer actually?
See,
when the boring tube
which converts one form of energy into other form.
Other form or electrical energy, when the conversion of one form of energy into electrical energy or vice versa?
Not specifically, electrical. One form to other will generally we'll call it transducer.
Okay, so boring tube gauge is an transducer. Boring tube pressure gauge. Boring tube pressure gauge.
I'm not getting. There is no clarity in your voice.
Boring tube pressure gauge, sir.
Boron,
boring tube gauge. Pressure gauge. Boring tube. Boring tube. Yes, boring tube pressure gauge. It is a transducer, right?
No, I'm because pressure gauge I don't know actually, because where you will use it, pressure gauge and other
gauge is an pressure energy conversion into the mechanical energy. So is it transducer?
Pressure is mechanical energy. What type of energy is pressure?
Pressure energy. I mean kinetic energy into pressure mechanical energy.
Where you will use this? Where you will use this?
Pressure gauge, sir. Boring tube pressure gauge.
That's what I'm telling you. Where you will use one? Can you tell me one application?
Application pressure gauge actually.
That's what. What's your name?
Yes. Yeah, I'm Vishnu. Sir.
Yeah. Where you will use? That's what I'm asking you. Depending upon that, I can clarify, because I'm very illiterate what you are talking, pressure gauge and all. Because I'm electronics background, no.
It's okay, sir. I'm in the section of MEMS and NEMS. You told that transducer is a conversion of one form.
So there is not only MEMS and NEMS, any device which converts one form of energy into other form, you can call it as transducer in general.
Okay.
I have given just to know there are many other devices where you can consider, because you need to integrate many things here, not only one part. In MEMS and NEMS, not only one, only electronics or only electrical is not possible. Mechanical, civil, everything will combine in there.
Okay.
So you should have a thorough of all the things.
Okay, sir.
Interdisciplinary, I can call.
Okay, sir. Thank you, sir.
Is it fine?
Yeah, fine, sir. Okay. Thank you.
Yeah. Yes.
Sir, I asked my doubts actually. I forgot to lower.
Yeah, lower your hand.
Yeah. I'm sorry. Yeah.
As I cannot identify here.
Okay.
There are many things. Okay.
Okay.
So those who got clarified, please lower your hands, please. Yeah, Chandu.
Hello?
Yeah.
Sir, am I audible?
Yes. Go ahead.
Sir, I have a doubt in switch.
Switch.
While you are talking about switch, you said that normal PN junction diode has only two terminals and
Yes.
it cannot act as a active element.
Yes.
Since it doesn't have a control terminal.
Obviously.
Sir, but in tunnel diode, there will be only two terminals, no sir?
Yes.
But here, negative resistance region, it acts. Does it act as a control element, sir?
No. That's what. See, any device which has VI characteristics, in VI characteristics negative resistance region, that can be used as an oscillator circuit. This is a basic principle.
Sir?
Any device which is having negative resistance region in VI characteristics, it can be used as an oscillator circuit. You know what is an oscillator?
Yes, sir.
Okay. So now I am getting energy, no? Oscillation means.
Yes, sir.
So where I am getting the energy, no? The first definition can be fitting for this. So once if you have the negative resistance, then I can call it. So that then we are not bothering about how many terminals are present.
Okay.
Hope I am clear.
Okay.
So the important property is what? You should have the negative resistance property in the VI characteristics. Then only you can call it. Is it fine?
Yes, sir.
Okay.
Thank you.
Yeah. Next, Stravya. Yeah, Manisha is there. Please unmute and ask the question.
Hello.
Yeah.
Sir, you clarified my doubt, sir.
Yeah.
And I
Then lower
lowered
your
my
hand.
hand off.
Please lower your hand. Huh?
Sir, I lowered my hand, sir.
Okay. Okay. Fine.
Okay, sir.
Shashidhar.
Hello, sir. Good afternoon. Am I audible, sir?
Yeah. Go ahead.
Sir, I have one general doubt. So, what is the difference between positive temperature coefficient and negative temperature coefficient, sir?
With respect to what?
Means respect to any components such as
Yeah, the name itself is giving no
resistor.
positive temperature coefficient means what? Any parameter is going to increase with respect to increase in temperature, then it is positive.
Okay.
Any parameter which is decreasing with increase in temperature, you can call it as negative.
Okay, means like they're opposite, we can say, sir. Like with the temperature increases.
Not like opposite. Don't use the general terms.
Okay.
Be specific, okay?
Yes, sir.
Because
Sir,
in
and-
some cases that will create lot of doubts.
Okay, sir.
Better we will be very certain what we are representing.
Okay, sir. Sir, sir, one more, sir.
Yeah.
Sir, in the PN junction diode, if we consider the diode as a forward bias, we can say that that the diode can be in the active, like the diode can also like act as what do you call active device, no, sir? Because
No.
in the
Active
forward
device
bias
means what?
means
That's
like
what-
in the forward bias, PN junction will actually act as a source of energy, no, sir. In the forward bias,
Where you are getting the source of energy?
in the forward bias, we'll get a
No. See, you are
get
applying a
potential
forward
voltage,
voltage,
sir.
no? You are
Yes, sir.
applying a forward voltage.
So that voltage can act as a source, no, sir. That the forward voltage.
Where see source means it has to drive or it should give to the some circuit where you can give it.
We can give to any resistor components or its capacitor.
No, man. See, and if you remember, even when you are giving the definitions of that, I very clearly mentioned it is not only the example we have given no for active devices. So what we have given that all the voltage and current sources, they are independent sources. Please try to understand this. They are not dependent. In that way, if you are whatever you are talking now, then I can take dependent sources also as an active.
Okay, sir.
Yes or no?
Yes, sir.
So these are independent.
Okay, sir. And then what is the control terminal, sir? There in the active device, you gave a one block diagram, input, output, and a control terminal. So what is the significance of control terminal, sir? There?
See, simple. You take the transistor. There are 3 terminals, no? Emitter, base, collector.
Yes, sir.
3 different configurations. So how you are, suppose you take common emitter configuration, your emitter terminal is going to be common for both input and output. Or simply I can say base current will decide your output current, no?
Yes, sir.
That is the control terminal there. I can say simply.
Okay, sir.
Is it fine?
Yes, sir. Got it.
Yeah.
Thank you, sir.
Yeah. Yeah, Shravya, please go ahead.
Sir, there's this transport of charge carriers and mobility of charge carriers.
Shravya, I'm not getting your voice.
Sir, now am I audible?
No, please speak louder. Very, very low voice I'm getting.
Okay. Sir.
Yeah.
Sir, this transport of charge carriers and mobility of charge carriers refers to the same, sir.
Transport of charge, please louder. Transport of charge carriers and mobility.
And mobility refers to the same, sir.
No, maybe, but there are a lot of difference here. Mobility, we'll talk. Drift velocity, we are going to talk. No, there will be difference. We'll see that.
Okay, sir.
In detail, we'll see that.
Okay, sir.
Okay. Any other doubts?
No, sir. No, sir.
Yeah. Ashwita, please go ahead.
Good afternoon, sir.
Good afternoon.
I am audible, sir.
Yes. Go ahead.
Sir, tunnel diode is an active device.
Yes. What's your doubt?
In GINA diode also active device, na, sir?
No. That's what, no. See, anyhow, 1 second. In the discussion that we made, we have very clearly mentioned how we are defining the different active and passive devices, no? So
Yes,
how
sir.
you define active device? Any device should fit to these 3 definitions. Either it can able to generate or give the energy to the external world, or it should perform the amplification, or it should perform the switching. But anyhow, diode can also be performing the switching, but still it is not. The reason are given. There is no control terminal that is going to be present. Is it fine?
Yes, sir.
Go ahead.
And another way you said, sir, if the negative resistance region is present in VI characteristics, then it is an active device. In GINA diode also there, na, sir?
Where you have negative resistance? GINA diode you don't have negative resistance, no?
Why, sir? In negative resistance only we use GINA diode as a voltage regulator.
No,
na,
it is
sir?
breakdown condition. Please try to understand. GINA diode will act as a voltage regulator under breakdown condition. It is not negative resistance. You are thinking that it is present in the 3rd quadrant, so it is negative resistance. Negative resistance means what? See, usually when you increase the voltage, what will happen to the current? When you increase the voltage, current should increase, no?
Yes, sir.
But with the increase in voltage, current is decreasing, then you will call it as negative resistance.
Okay, sir.
So it's not like maybe you are thinking that it is in the 3rd quadrant, so it is in the negative resistance. No.
Yes, sir. I had doubt. I searched in Google also, sir.
Okay.
GINA diode is active only showing Google also.
It is showing active.
Active. Yes, sir. GINA diode is active.
Okay. So on what basis he has given?
The negative resistance property.
Oh, where it is? Okay. Let me check and I'll clarify. Okay.
Okay, sir.
Up to my knowledge, I think it is not. GINA diode cannot be considered as an active. Okay. Let me check.
It has also 2 terminals only, sir. In that control terminal is not there, na, sir, in GINA diode.
Obviously.
Yes,
There is
sir.
no control terminal.
In that way also, GINA diode is active, na, sir.
No, control terminal should be there if you want to call it as active.
Yes, sir.
Where the control terminal is there for GINA diode? There are only 2 terminals, no?
Yes, sir. Yes, sir. I confused. Okay, sir.
Am I clear?
Yes, sir.
Yeah.
Sir, in another electroluminescence.
Another, please be louder.
Electroluminescence.
Electroluminescence. Yeah.
You can observe in only direct band gap semiconductors, na, sir?
Yeah, obviously.
In what is the specification of direct band gap semiconductors and
Yeah, we'll go for in detail discussion about what is direct band gap and indirect band gap later. Don't worry. Okay.
okay, so how is it depend on the h mu, sir?
H nu is what? Photon energy. No, you are
Yes,
making
sir.
the light energy to fall.
Yes, sir.
That is intensity of light. Your photon energy, light
Yes,
energy.
sir. That is in the output then, sir. Light energy, we get the output as light energy. So we said that E is equals to h mu.
Hmm? No,
Output is light
is
energy in
the
electroluminescence, na sir?
electroluminescence. Your output is light energy. What about
Yes,
input?
sir. Input also electron hole pair, na sir?
How you are getting that that is what. See, this point also electroluminescence and photoluminescence. Again, we will discuss in the LED, light emitting diode. How you are exciting the electron hole pairs? No, how you are getting the electron hole pairs? Depending upon that, either you can have electroluminescence or photoluminescence also.
Okay, sir.
Okay.
Any connection between direct band semiconductors and light energy sources, sir?
Obviously, that's what I'm telling you. Whatever I have given here, this luminescence process can be observed only in the
Direct band gap semiconductor.
you cannot observe this in indirect. In indirect also there will be recombination, indirect semiconductors also, but that will be dissipated as heat energy. You cannot see the light.
Okay, sir.
Fine.
Okay, sir. Sir, another one.
Yeah.
In photoluminescence, you said that usage examples.
There are some practical applications because we don't
Yes, sir.
require in our course. That's why I'm not discussing. But in the case of electroluminescence, we need to discuss about light emitting diode and laser. No.
Yes, sir.
That's why I've given. You can go ahead. You can explore this.
I searched, sir, for photoluminescence examples. In that embroidered thread is photoluminescence is there, sir.
Which one?
Embroidered thread.
That's why there are many applications. Okay, but that is not required for us. That's the reason why I'm not discussing here.
Okay, sir.
For
Okay.
your examination also, I think they will not give any question from this.
But I have one doubt, sir. In embroidered thread, how is it possible photoluminescence, sir? In photoluminescence, I searched one example, sir. In that embroidered thread is there.
Okay,
I have
not
general
seen.
doubt.
That's what I have not gone through that example. Okay.
Okay, okay. Thank you, sir.
Fine.
Okay, sir. Thank you, sir.
Okay. Satvik, please go ahead.
Hello.
Yeah.
Am I audible, sir?
Yes, yes.
So, as you said, ambient conditions are two types: temperature and illumination. Suppose I say ambient temperature is nothing but as a surrounding temperature. Am I right, sir?
Yes, ambience is
So,
nothing but what? Surrounding.
can you give an example for that?
Example means what? I'm not getting your question.
I think it is signal to noise ratio, nothing but surrounding temperature is nothing but as a noise. Let us consider.
No. Why? Where you are finding signal to noise ratio? I'm not sending any signal here.
Suppose, and let us consider it is a surrounding temperature as a noise.
Please, one second. Don't overlap or get many things into one topic which is unnecessary. You just
Sir, I have another
so that
doubt.
you will get lot of confusion. Please, you will get lot of confusion.
Okay, sir. So I have another doubt.
No. Wait. Let me clarify the first one.
Okay.
See, ambience is what? Suppose I am sitting in a room. What is my ambience? Physically, you may see many things, but there is a temperature, no?
Yes, sir.
Okay. So that is what I have written there. Whatever the device that you are operating, certainly there will be some temperature which is surrounding that device.
Yes, sir.
Now, this also influences the characteristic.
Sir, every device is having ambient temperature.
Obviously, that's what. See, suppose you are using your remote, TV remote
Yes,
is there,
sir.
no?
Yes, sir. Yes, sir.
Internally, you have some electronic devices also. Let's
Yes, sir.
say character diode will be there.
Yes, sir.
there will be certain temperature, no? Wherever you place surrounding that, there will be certain temperature, which is the ambient temperature.
Okay, sir.
Fine.
Okay, sir. Thank you, sir.
Go ahead. Next question.
Sir, in metals, free electron concentration is very high, sir. So in metals, free electron concentration is independent of temperature or dependent of temperature, sir?
It is dependent concentration, you can say dependent, but not, considerably you cannot change anything there.
So if we increase the if we increase the temperature, the conduction band and valency band are overlapped, sir. Overlap also increases now, sir.
May not be you may not think in that way, but what will happen is usually when you increase the temperature, the mobility is going to decrease actually.
Oh.
See, for a conductor, if you increase the temperature, what will happen to the resistance?
Decreases.
What?
Decreases.
No, increases. For a conductor, if you increase the temperature, resistance is going to
okay, sir. Okay.
But semiconductor, it will decrease. And not
okay,
for
sir.
all the range of temperatures also.
Okay, sir.
It's not general, okay? See, why it is decreasing is when you increase the temperature, mobility is going to decrease. And that mobility makes your, resistance or conductivity.
Hello?
Yeah. Are you able to hear me?
Yes, sir.
When you increase the temperature, mobility is decreasing. Because of that, conductivity decreases. I'm talking about the conductor.
Okay, sir.
And because of decrease in conductivity, resistance is going to increase.
Okay, sir.
Is it fine?
Okay, sir. Thank you, sir.
Okay. Yeah, Rohit, please go ahead.
Good afternoon, sir.
Good afternoon.
Sir, you said energy of the conduction band is higher than the energy of the valence band. Is it right, sir? But energy of the conduction band is higher than the energy of the valence band. But in metal energy gap band diagram, you have shown EV is above than EC. Why is it like that?
There is an overlap. That's what. Yeah, this you may get clarified one where we are going to discuss about the energy band model. Okay. So here I have directly represented the energy band diagram. We don't know. I have not explained how you are getting this energy band diagram. Later, when you are considering the energy band diagram, we will discuss how this energy band is going to form.
Okay, sir.
Okay. So there you can better understand this.
Okay, sir. Thank you.
Are you getting my question? My answer?
Okay. Yes, sir.
Yeah, we'll discuss this in detail. Don't worry.
Okay, sir. Thank you.
Yeah, Akhila Reddy, please go ahead.
Hello, good afternoon, sir.
Very good afternoon.
Sir, you said at temperature greater than 0 Kelvin, the electron pair generation takes place or recombination takes place?
Yes. Yeah, what is your doubt in that? How it is going to happen? Huh?
The generation and recombination can't be taken place at a time, no, sir. So which one occurs at temperature T?
Yeah, I got your question. See, how many electrons are present? Suppose you take, I have given semiconductor, it will be range of 10 power 6 per centimeter cube to 10 power 21. No, let us assume there are 10 power 15 electrons per centimeter cube.
Okay, sir.
Okay, in a semiconductor material.
Okay.
Then you have intrinsic concentration. Based on that, you can get the whole concentration also.
Yes, sir.
Is it fine?
Okay.
Now, it is not one electron, one hole. Please try to understand this point.
Yes, sir.
So, suppose one electron is moving from valence band to conduction band. At the same time, another electron can move from conduction band to valence band.
Okay.
Are you getting?
So,
I'm not saying that same electron hole pair is simultaneously having the generation and recombination. There are different electrons and different holes. Are you getting my point?
It means energy of all the electrons can't be same.
Obviously, no.
Okay.
Because conduction band also, so where you are going to place this depends on how much energy you are giving for the valence electron.
Okay, so it means will all the conduction band electrons can't have same energy?
Yeah, how it can be, no? Because if you see the energy band diagram that we have drawn, Y-axis represents what? Electron energy, no?
Yes, sir.
Okay. So there will be discrete levels, but they are going to be continuous. Sorry. Discrete, but still they are continuous.
Okay, sir.
Maybe this doubt you might get clarified when you are discussing about the how the energy band is going to form. This conduction band and valence band are going to form. Maybe at that point of time you will get clarified.
Okay.
Or simply I'll give. Suppose you take a one atom, individual atom, okay, isolated atom.
Okay, sir.
So you'll have the ground level, then
Yeah.
other energy levels also.
Yeah. Okay. I got
Now
it, sir. Now I got it.
how to form the crystal? You decrease the interatomic distance between the atoms, and you have to form.
Yes.
So when they are coming to close, atoms are coming very close. What will happen? The valence electrons are going to start interacting. No.
Yes, sir.
You know what is the Pauli's exclusion principle? No two electrons should have the same energy.
Same energy. Yeah.
So there, what will happen is these discrete energy levels are going to form continuous energy levels as the band.
Okay.
Are you getting?
Yes, sir. Yes, sir.
Yeah.
And semiconductor devices are having negative temperature quotients, no, sir?
Yeah,
Towards
not
resistance.
for all the temperature range. It's
So T equals to 0 Kelvin, then at this range, what is the condition for
equal
resistance
to
and
0
temperature?
Kelvin. Come again.
So at T equals to 0 Kelvin or at T greater than 0 Kelvin in some.
Yeah, don't worry. Still, we have not started the actual content. No, we'll discuss. Huh?
So there, what is the condition between temperature and resistance, sir? At 0 and few values above the 0.
That's what I'm telling you. When you keep on increasing the temperature, we are going to consider there is if you take intrinsic semiconductor, definitely resistance is going to decrease. But extrinsic semiconductor material, it's not going to decrease continuously.
Okay.
There will be certain value where it's changing. Yeah, these things you'll get clarified once you complete semiconductor theory. Don't worry. Okay, these points we'll address.
Okay. Okay.
Fine.
Thank you, sir.
Yeah. Yeah, Manjari Gupta, please go ahead.
Hello.
Yeah.
Good afternoon, sir.
Good afternoon.
Sir, I wanted to ask that in among the points that you have listed in the syllabus, which one are necessary for instrumentation students?
Instrumentation, what you are writing, gate or ESC?
Gate.
Yeah. Here for gate also, my point here is you are going to have analog electronics in your syllabus.
Yes, sir.
Yeah. Then analog electronics means what? Application of the devices. Yes, sir.
Yes, sir.
So then, if you want to understand the applications, you must know characteristics of the devices, no?
Yes, sir. No, sir, but I am asking that among these topics, we are going to study some certain few topics, right, sir? Because class are till 2nd June. So we are
Certain
not going to
topics
study
means-
full EDC.
No, I'm not getting. Certain topics means
So
that is what I'm explaining you. See, your device is made up of what? Semiconductor material, no?
yes, sir.
Then if you have better understanding of semiconductor material, you can better understand the device. If you have better understanding the device, you can better understand the applications.
Okay, sir.
Am I clear?
Yes, sir.
Yeah. Yeah, Divyagna, please go ahead.
Hello, sir. Can you hear me?
Yeah.
Sir, you said reliability means that for a particular input, the output will
Yeah,
be
please be louder.
Hello, sir. Can you hear me now?
Yeah. Reliability.
Yeah, reliability means for a particular input, the output will be constant irrespective of the surroundings, no, sir.
Yeah, please. I'm not getting your voice clearly. There is a disturbance.
Sir, can I mail you the doubt?
No, you can ask me. No, don't worry. You just be louder.
Yeah, sir. For reliability means for a particular input, the output will be constant irrespective of the surroundings, no, sir.
No, it's not only input and output here. Suppose suppose you are using a switch, for example.
Yes, sir.
Okay, and under certain condition, you need to switch off. Okay, it is in the on condition. You want to switch it off.
Yes, sir.
Okay, there will be some, you know, threshold and all you have given automatically, it has to switch off if conditions are changing or particular way.
Okay.
Even though conditions are changing, your switch is not, you know, it is still in the on condition. So there can be a lot of damage with that. That type of reliability we are talking.
Yes, sir, but semiconductors are sensitive to temperatures, no, sir?
Obviously.
Then how can it be more reliable?
Yeah, that is what. There will be range of temperatures your device can be operated. That is important here. It's not for a particular one value of temperature. It's a range of temperature. So within that range, it can be applicable.
And so one more doubt. While manufacturing, which one is preferable, sir, germanium or silicon?
While manufacturing, yeah, they have their merits and demerits, but silicon is going to be available, maybe not directly, okay, as a sand, and then from that they are going to extract. And in many applications, silicon is preferable. We'll discuss that point later, okay? Why silicon is preferable than the germanium? When we are, you know, as we are going on discussing these topics, you can get clarified. There are many parameters and many constants that you have to consider.
Okay, sir.
Not
Thank you.
with one simple point. Okay?
Yes, thank you, sir.
Yeah. Yeah, Charishma, please go ahead.
Sir, no doubt.
Yes?
No doubt, sir.
So then lower your hand, please.
Okay, sir.
Yeah, Divyansh, please go ahead. Divyansh. Sai, please go ahead.
Hello, sir.
Yes.
Am I audible?
No, be louder, please.
Sir, am I audible now?
Yeah, you have to speak louder.
Sir, am I audible now?
Not much.
Sir, good afternoon, sir. Now?
Yeah, fine. Go ahead.
Sir, I have a general doubt that
Yeah.
what type of questions will be asked in GATE exam regarding EDC? More number of problems or TD questions like that?
For which GATE or ESC?
GATE exam, sir.
GATE exam. See, not only EDC, in GATE exam, most of the things, that is 70 to 80% numerical problems. Okay.
Sir.
And 20 to 30% you'll get the theoretical questions. Whereas in ESC, it is a different scenario. Okay, almost 50 to 60% you may expect the theoretical questions, and other part will be numerical.
Okay, sir.
Yeah, whether it is whether it is numerical or theoretical question, you must have the understanding of the subject first to answer anyone. Yes or no?
Yes, sir.
Yeah.
Sir, what should be our preparation strategy for GATE exam, sir?
You are in which year now?
Third year completed, sir.
Third year completed. Okay. So preparation strategy, you should have, first that's what I have given. No, two factors will decide your rank. One is the speed, the other one is the accuracy. Okay. To improve these two, first you have to get thorough with the concept. Nothing but you can listen to any expert. Okay. Anyhow, you are taking the coaching, so you need to listen with concentration. That is important. You are not supposed to miss any point, single point also. And then you start practicing. This is very, very important, where students are lagging actually. They don't practice. Initially, they are not listening to the class itself. And another one, there is no practice. If you don't practice, see, anything that you are doing, new things that you are doing, you are bound to do some mistakes. From that mistakes, you should be able to get the subject. So if you are not practicing, these mistakes will happen in the examination. Okay. And for each subject, okay, so you may prioritize. One is easy, one is difficult. This is only you made up of your mind, which is easy, which is difficult. Okay. So when you listen to the class, almost from each subject, at least one question you can easily answer. At least one, without any preparation, just listening to the class, at least one question you can very easily answer. Okay. So on an average, you will have, 10 subjects, 10 questions you can be very easily answer. Then with a little, effort, another 1 to 2 questions, almost 30 marks you can get very easily. So you can easily qualify. But after that, each thing is going to be matter. It's going to be your effort. Okay. So there should be continuity of your preparation, please, because you may prepare for today for 10 hours and 1 week you are not studying. Again, next 2 days you are studying for 10 hours per day. Again, 1 month you are not studying. This will not help you definitely. How much knowledge you are going to have. There should be regular practice. Suppose you fix morning 6 to 8, you have to study, then you have to study. There is no other option. You have to study every day 6 to 8. In that way, you have to control yourself and you have to do. Then definitely over a period of time, there will be considerable amount of improvement in you. Okay, is it clear?
Yes, sir.
Right?
Okay, sir. Thank
Okay.
you.
Yeah, any other doubt?
No, sir.
Okay, all the best.
Thank you, sir.
Yeah. G. Krishna, please go ahead.
Hello, sir. Good afternoon, sir. Can you hear me? Hello.
Yes, go ahead.
You told that light immune is photoluminescence is caused only in direct band semiconductors, right, sir?
Please be louder. Be louder.
Hello, sir. Hello.
Yeah. Direct band gap semiconductor. Okay.
So in indirect band semiconductors, you told that it is dissipated in the form of heat, right?
Yes.
So resistor come under indirect band semiconductor, sir?
Resistor here it is not component. No, I am talking about the material. You are talking about the component. Resistor is made up of which material? That is important for us now.
Okay.
Are you getting my point?
Yes, sir. Yes, sir.
See,
yes,
resistor
sir.
is a component. I am talking about the material. There is a lot of difference.
Okay, sir. Thank you, sir. That's it, sir.
Uday Kiran, please go ahead. Uday Kiran.
Hello, sir. Can you hear me?
Yeah, please.
Sir, actually, I have a practical doubt that in the start of the lecture, you have told that we can make insulator to
Please
conduct
be
by.
louder. Be louder, please.
Hello.
Be louder.
Sir, can you hear me?
Yes. I'm here. I can able to hear you, but be louder.
Sir.
Go ahead.
Now
go
you
ahead.
can hear.
Yeah.
Sir, actually, in the start of the lecture, you told that insulator can be made as a conductor by giving.
No, I didn't say by you can make it as conductor.
Like it can conduct.
To give 6 electron volts of energy, then it can enter into the electron can enter into the where conduction band.
Conduction band, like it can conduct, sir, right? Then if we can give 6 electron volts of energy, it can conduct.
Fine. What is your doubt?
But you told that the material cannot sustain that 6 electron volts of energy. Hello?
Yes, it cannot withstand.
But the thing is that 1 electron volt is very less energy, sir. 6 electron volts. Sorry?
1 electron volt and 6 electron volts, if you are talking, it is a relative term.
Okay.
Yes or no? 1 electron volt is less than 6 electron volts. It can easily, this 1 electron volt can be withstood by the material.
Yes, sir. 6 electron, even if 1 electron volt is very less, 6 electron volts is also like relatively very less.
That's what I'm talking, man. Relative term, 6 electron volts is less for you.
Yes, sir.
Not for the material. Suppose, see, if I'm a 60 kgs, I can bear 60 kgs. If you 65 kgs also, it's going to be difficult for me. The maximum is 60 kgs. If you put 61 also, it's going to be difficult. So it is a relative term.
So it if we can I mean we can give the energy, but the electron cannot sustain that kind of energy.
Yeah, electron or material cannot sustain. Yes.
Okay, sir. Thank you.
Fine.
Sir. Yeah.
Purnima, please go ahead.
Hello.
Yeah.
So you were able to hear my voice?
Yeah, yeah. Go ahead.
Hello. Sir, I have one general doubt.
Okay.
It's like, is there any textbooks available so that we can start solving the problems, not for referring?
Hmm.
If we are able to solve the problems from that textbook, then we'll be okay for
Yeah,
PSC.
I'll definitely give the list of textbooks. Don't worry. But
Okay.
my sincere request is, see, by referring all the textbooks and other material, we have structured this course.
Okay.
On
So
behalf
not
of
about
you.
referring,
No,
just
one
solving
second.
problems.
Let me complete. Okay. So
Okay.
what we are going to do is, those things will give for practice purpose. Initially, you start the previous questions and the practice questions are given for
Yes, sir.
You do that.
Okay, sir.
Okay. And anyhow, I think maybe tomorrow I'll give the list of textbooks. Don't worry.
Okay, sir.
Okay. But my sincere advice is, at the beginning, don't go for any textbook, because see, if you take one standard textbook, you will take.
Okay.
If he's starting one particular topic, there will be introduction will be there. After introduction, he will enter into the actual topic, and then he will go to the application part.
Okay.
So in the core, if you go and read the core part, excluding your introduction, there will be a lot of doubts that you are going to get.
Okay.
Okay.
Okay, sir.
What we are going to do here is that gaps we are going to fill initially.
Okay.
See, suppose you take EDC, electronic devices and circuits by Millman and Halkias. Have you heard this textbook?
Oh, yes, sir. Millman's. I heard this.
Heard? So if
Yes,
you
sir.
go and directly, read some content in that, at the beginning, okay, you may not in a position to understand what actually they are telling.
Okay.
That is the reason why I'm skipping, but I'm not telling you that don't go for the reference books.
Okay.
Right, okay?
Okay.
Not now, not initial stage.
Okay.
Anyhow, I'll give the reference books. Don't worry, okay?
Okay, sir.
Okay.
Thank you, sir.
Yeah. Yeah, Divyansh, please go ahead. Please unmute your voice and go ahead. Yeah, those who got doubts clear, please unmute your voice. Please, Divyansh Kanchan Saxena, please unmute your voice and raise your doubt. Divyansh Kanchan Saxena, please unmute your voice and ask the doubt. Divyansh Kanchan Saxena, please unmute your voice and ask the doubt.
So you already cleared my doubt. You're unmuted.
You got clarified?
But I'm not Divyansh, I'm Divyagna.
Hello.
Yeah.
Hello, sir.
Yeah, Divyansh.
So can you hear me?
Yes. Go ahead.
Sir, I want to ask that the syllabus that you are covering, I am from Gate Instrumentation stream.
Okay.
So are you going to cover transistor portion for us, sir?
Anyhow, this is common for even EC also, no? Transistor will be there.
Okay, sir.
Diode,
and the
diode,
analog
transistor
portion,
will part, yes.
like clippers and all kind of stuff.
Uh-huh.
Basics for analog. Instrumentation stream don't have EDC subject, but are you covering all these portions that are important for numerical solving?
Numericals, anyhow, I'll discuss now. Obviously, I'll discuss the numericals.
Okay, sir. Thank you, sir.
Okay. Yeah, any more doubts?
Cleared, sir. Cleared, sir.
Okay, fine. You unmute your voice, please.
Yes, sir.
Yeah. Dear students, any more doubts? Okay, we'll meet tomorrow. Okay.